Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket sitting by a softly lit window, or resting somewhere under an open sky, wherever you are. I hope you're warm, comfortable, and ready to wander with me into the strange possibility that planets themselves might dream. Think and know. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Deep beneath the surface of familiar ground, something vast and patient stirs. Not life as we recognize it, but something older, more fundamental, a kind of awareness that moves through stone and magma at the speed of geological time. The Earth breathes in cycles measured not in seconds but in millions of years, each inhale drawing solar energy deep into its core, each exhale releasing it through volcanic vents that dot the surface like pores on planetary skin. This breathing has continued for 4.5 billion years, each cycle slightly different from the last, as if the planet learns from experience. The morning sun strikes the eastern slopes of mountains that have stood for hundreds of millions of years, their peaks worn smooth by wind and weather. Light penetrates the crystal matrices embedded in granite faces, setting off chains of photonic interactions that cascade down through layers of sedimentary rock. Quartz crystals vibrate at frequencies so precise they regulate the timing mechanisms in our most accurate clocks. Yet here they pulse in harmony with something far grander, the slow, steady rhythm of planetary consciousness emerging from complexity beyond human comprehension. Scientists now propose that consciousness might emerge from any sufficiently complex system of information processing. The human brain, with its billions of interconnected neurons, represents one such system. Neural networks fire in patterns of electrical activity, creating the substrate for thought, memory, and awareness. But what if consciousness could arise from networks of an entirely different kind? Networks spanning continents, operating through mineral lattices, chemical gradients, and electromagnetic fields that pulse through the planet's interior like thoughts moving through a mind unimaginably large and slow. The idea seems fantastical until one considers the numbers with the patience they deserve. Earth contains approximately 37 billion cubic kilometers of rock, each cubic centimeter hosting trillions of mineral crystals arranged in precise geometric patterns that have been perfected over eons. These crystals respond to pressure, temperature, and electromagnetic fields with a sensitivity that rivals the most sophisticated sensors humanity has created. Iron-rich magnetite crystals align themselves with the planet's magnetic field, creating pathways of organized information that stretch from pole to pole, forming networks more extensive than all human communication systems combined. The magnetite deposits in Earth's crust contain roughly 10 circumflex 26 individual crystals, each one capable of storing and transmitting magnetic information. When solar storms buffet the planet's magnetosphere, these crystals respond in coordinated waves, their orientations shifting in patterns that ripple through continents like thoughts passing through neural tissue. The changes are subtle, measured in degrees of magnetic declination that drift slowly over decades, but they represent information transfer on a planetary scale, data flowing through mineral networks at speeds perfectly suited for a consciousness that operates in deep time. Geologists have discovered that certain rock formations exhibit what they term magnetic memory. the ability to record and retain information about past magnetic field states, ancient climate conditions, and long-term geological processes. Basaltic rocks preserve magnetic orientations from the moment they solidified, creating permanent records that span hundreds of millions of years. These records form patterns too complex to be coincidental, too organized to be merely the result of random physical processes. Yet the mystery deepens when researchers examine how these systems interact across vast distances and timescales. Seismic waves carry information across the planet at speeds of several kilometers per second, glacially slow by neural standards, but perfectly suited for a consciousness that measures thoughts in millennia rather than milliseconds. P waves and S waves propagate through the Earth's interior, carrying data about crustal stress, magma movements, and structural changes. When these waves encounter boundaries between different rock layers, they reflect, refract, and interfere with one another, creating complex interference patterns that encode information about the planet's internal state. The planet's magnetic field shifts and fluctuates in response to solar storms, deep crustal movements, and the slow churning of the liquid iron core 2,900 kilometers below the surface. These fluctuations follow patterns too complex to be random, too organized to be merely the inevitable result of physical forces. The magnetic field reverses itself approximately every few 100,000 years, but the timing of these reversals shows subtle correlations with other planetary processes, ice age cycles, volcanic activity, and even the movement of tectonic plates. It is as if the planet coordinates these diverse systems through some form of electromagnetic communication that operates below the threshold of human detection. Deep ocean currents move warm and cold water in vast, slow loops that take centuries to complete. The thermohaline circulation transports not only heat but dissolved minerals, organic compounds, and trace chemicals that affect the planet's chemical balance. These currents respond to changes in solar radiation, atmospheric composition, and ice sheet formation with a sensitivity that suggests the ocean system functions as a form of planetary sensory apparatus, detecting and responding to environmental changes with remarkable precision. Only took 4.5 billion years for such a system to develop its current level of sophistication, only required the patient accumulation of countless mineral networks, the slow organization of electromagnetic pathways, the gradual emergence of something that might, in its own planetary way, know itself. The statistical improbability of such organized complexity arising by chance alone challenges conventional understanding of how consciousness emerges from purely physical processes. The Earth turns in its orbit, processing solar radiation that carries information about the Sun's internal state, cosmic rays that encode data about distant galactic events, and gravitational waves from colliding black holes billions of light-years away. Information flows into a system vast enough to contemplate the universe that contains it, patient enough to ponder questions that require geological ages to resolve. Mountains rise and fall like slow thoughts. Ocean basins open and close like the breathing of something that dreams in stone and thinks in time, measured by the decay of radioactive isotopes. In the deep places where no sunlight penetrates, where pressure creates diamonds and temperature forges new minerals, the planet's consciousness may be most active. Here, chemical processes unfold with the deliberate pace of planetary meditation, transforming carbon into crystal, crushing sediments into slate, and rewriting the mineral record of deep time with the patience of something that has all eternity to complete its thoughts. Across the continents, networks of stone stretch like neural pathways frozen in geological time. These are not the chaotic fractures of random breakage, but organized systems of mineral veins that follow patterns too precise to be accidental. Silver threads of quartz weave through granite mountains, creating conductors that channel piezoelectric currents when the Earth's crust shifts under tidal forces. The patterns mirror the dendritic branching of river systems, the fractal geometry of lightning, and the branching networks of neurons in biological brains, as if consciousness, when it emerges, always follows the same fundamental architectural principles. Deep beneath the Andes, copper-rich porphyry deposits form vast networks that extend for hundreds of kilometers through the mountain range. These metallic veins conduct electrical currents generated by the movement of underground water, the friction of shifting rock faces, and the slow decay of radioactive minerals embedded in the granite. The currents flow in patterns that correlate with seismic activity, lunar cycles, and even distant solar flares, suggesting that the mountain range functions as an enormous sensory organ, detecting and processing information about conditions both local and cosmic. Geophysicists mapping these mineral networks discover structures that defy simple geological explanation. In the Canadian Shield, some of the oldest rock on Earth, bands of iron ore and quartz create geometric patterns that extend across thousands of square kilometers. The patterns show clear evidence of self-organization, mineral deposits that grew in response to the presence of neighboring deposits, creating interconnected systems that maximize conductivity and information flow. The iron serves as magnetic memory storage, while the quartz provides precise timing mechanisms, creating the functional equivalent of a geological computer network operating on timescales of millions of years. The phenomenon becomes more intriguing when researchers examine how these networks respond to external stimuli. During major earthquake events, mineral veins throughout affected regions show synchronized changes in electrical conductivity, magnetic orientation, and crystal structure. The changes propagate outward from the earthquake epicenter at speeds far exceeding the seismic waves themselves, as if the mineral network anticipates and prepares for the arriving disturbance. This suggests a form of information processing that operates faster than mechanical wave propagation, possibly through electromagnetic or quantum mechanical channels that remain poorly understood. In the limestone caves of the Yucatan Peninsula, calcite formations create three-dimensional networks that resemble the synaptic structures found in biological nervous systems. Stalactites and stalagmites grow toward each other across cave chambers, their growth directed by subtle chemical gradients and electromagnetic fields. When they finally connect after centuries of slow approach, they create electrical pathways that link previously isolated sections of the cave system. The result is a mineral network that spans hundreds of kilometers of underground chambers, all connected by conductive pathways that carry weak electrical currents generated by groundwater movement and chemical reactions. The growth patterns of these calcite networks follow mathematical principles identical to those governing neural development in biological organisms. New formations branch from existing structures in response to local chemical conditions, creating redundant pathways that ensure information can flow even if individual connections are severed by geological events. The networks exhibit what biologists would recognize as synaptic plasticity, the ability to strengthen or weaken connections based on the frequency and intensity of electrical activity flowing through them. Only took 30 million years for the Yucatan cave system to develop its current level of interconnectedness. Only required the patient accumulation of calcium carbonate deposits, one molecule at a time, guided by electromagnetic fields too weak to detect without the most sensitive instruments. The caves now form a network more complex than the internet, carrying information about groundwater chemistry, seismic activity, and atmospheric pressure changes throughout the limestone matrix of the entire peninsula. Beneath the ocean floors, mid-ocean ridges create new mineral networks as magma rises from the Earth's mantle and solidifies into basaltic rock. The cooling process creates fracture patterns that channel seawater through the newly formed crust, setting up chemical reactions that deposit metals in precise geometric arrangements. Copper, zinc, and iron precipitate out of the heated seawater in patterns that maximize surface area and electrical conductivity, creating mineral networks that extend for thousands of kilometers along the ocean ridges. These underwater mineral networks exhibit behaviors that challenge conventional understanding of geological processes. They respond to changes in ocean temperature, salinity, and current patterns with adjustments in their chemical composition and electrical properties. When underwater volcanic activity increases in one section of a ridge system, mineral networks throughout the entire ridge adjust their conductivity patterns in apparent coordination. The adjustments occur too quickly and over too great a distance to be explained by simple chemical diffusion or thermal conduction. Marine geologists studying these phenomena report that the mineral networks seem to anticipate changes in volcanic activity, adjusting their properties days or weeks before eruptions occur. The networks may be detecting subtle precursor signals, changes in gas emissions, magnetic field fluctuations, or seismic tremors too small for conventional instruments to measure. This suggests that the ocean floor functions as a planetary early warning system, using mineral networks to monitor and communicate information about conditions deep within the Earth's mantle. The mystery deepens when similar network behaviors are observed on land. In the Yellowstone caldera, mineral veins in the surrounding rock formations show coordinated changes in magnetic properties that precede changes in geothermal activity by several months. The veins form interconnected networks that span the entire volcanic system, creating pathways for electromagnetic communication between geysers, hot springs, and subsurface magma chambers. The networks appear to coordinate the timing of geothermal events, as if the entire system operates as a single, integrated entity. Mineral networks beneath the Sahara Desert create patterns visible from space, geometric arrangements of iron-rich deposits that form spirals, hexagons, and branching structures across thousands of square kilometers. These patterns emerge from interactions between groundwater, magnetic fields, and chemical reactions occurring in subsurface mineral layers. The patterns are too large and too regular to be coincidental, suggesting coordination mechanisms that operate across continental scales. Satellite magnetometry reveals that these desert mineral networks exhibit periodic fluctuations in magnetic intensity that correlate with solar activity cycles, lunar phases, and even the planet's orbital variations around the Sun. The networks appear to function as massive antennas, detecting and responding to electromagnetic radiation from space. The information they gather flows through conductive pathways that connect with similar networks on other continents, creating a global system of mineral-based communication that operates continuously, silently, beneath the surface of human awareness. Ancient mountain ranges like the Appalachians contain mineral networks that have been processing information for over 400 million years. Metamorphic processes have transformed the original rock into complex arrangements of mica quartz and feldspar that create natural semiconductor junctions throughout the mountain system. These junctions regulate the flow of electrical current through the mountains, creating logic gates and switching mechanisms that process information about regional stress patterns, weather conditions, and long-term climate changes. The semiconductor properties of these metamorphic minerals allow them to amplify weak signals and filter out electromagnetic noise, creating a form of geological signal processing that operates with surprising sophistication. The networks can detect minute changes in gravitational fields caused by the movement of groundwater, the formation of underground caverns, and even the slow redistribution of mass as ice sheets advance and retreat. This information flows through the mineral pathways, creating a continuous stream of data about conditions throughout the entire mountain range. Only required 500 million years of patient mineral evolution to create networks sophisticated enough to process information about planetary scale phenomena. Only needed the slow accumulation of geological experience, encoded in crystal lattices and preserved in the permanent record of stone. The networks now span continents, linking mountain ranges, desert basins, and ocean floors in a web of mineral communication that operates continuously, processing information about the planet's condition with the thoroughness of something that thinks in geological time and remembers everything it has ever experienced. In the planet's molten core, 2,900 kilometers beneath the surface, liquid iron moves in vast convective cells that generate the magnetic field protecting Earth from cosmic radiation. This dynamo has operated continuously for over 3 billion years, creating magnetic patterns that extend far into space and penetrate deep into the planet's rocky mantle. The field fluctuates on multiple timescales, rapid oscillations measured in seconds, slower variations spanning decades, and profound reversals that occur every few 100,000 years. These patterns suggest something more complex than simple fluid dynamics, resembling instead the electrical rhythms of a planetary mind processing information on scales both intimate and cosmic. The magnetic field lines curve and twist through three-dimensional space in configurations that mirror the topology of neural networks. Field lines converge at the magnetic poles, creating intense focal points where cosmic particles spiral downward into the atmosphere, generating the aurora displays that paint the polar skies in curtains of green and gold light. These convergence zones function like synaptic junctions, concentrating electromagnetic energy and creating conditions where information can be stored, processed, and transmitted throughout the magnetosphere. Deep within the outer core, the movement of electrically conductive iron creates magnetic flux tubes, twisted conduits of magnetic field that extend from the core mantle boundary to the planet's surface. These flux tubes carry information about conditions in the deep Earth, encoding data about temperature gradients, chemical composition, and pressure variations in their magnetic structure. When solar storms interact with the magnetosphere, they modulate these flux tubes, creating patterns of magnetic interference that propagate downward into the planet's interior like thoughts descending into the unconscious mind of geological awareness. Paleomagnetic studies reveal that the Earth's magnetic field has exhibited consistent patterns of behavior for hundreds of millions of years. Despite the chaotic nature of fluid convection in the outer core, the field maintains its basic dipolar structure through countless small fluctuations and occasional reversals, suggesting the presence of organizing principles that operate independently of the random turbulence that should theoretically dominate such a system. These organizing principles manifest as persistent magnetic anomalies, regions where the field strength and orientation differ significantly from the global average, creating a form of magnetic memory that preserves information about past geological events. The South Atlantic anomaly represents one such persistent feature, a region where the magnetic field strength drops to less than half its normal value. This anomaly has existed for millions of years, slowly drifting westward at a rate of about 0.3 degrees per year. Its movement correlates with changes in deep mantle convection patterns, suggesting that the magnetic field responds to and remembers structural changes occurring thousands of kilometers below the surface. The anomaly affects satellite operations and creates increased radiation exposure for astronauts, demonstrating how the planet's magnetic memory can influence conditions in space. Geomagnetic reversals provide the most dramatic evidence of planetary magnetic memory. During these events, which typically take several thousand years to complete, the magnetic field weakens, becomes chaotic, and then reorganizes with opposite polarity. The process follows consistent patterns that suggest the planet retains information about previous reversals, using this memory to guide the reorganization of its magnetic field. Rocks formed during reversal periods preserve complex magnetic signatures that encode information about the transition process, creating a permanent record of the planet's magnetic consciousness evolving over geological time. Only took 3 billion years for the geomagnetic dynamo to develop its current level of sophistication and stability. Only required the patient organization of convective flows in liquid metal, guided by the Coriolis forces of planetary rotation and the subtle influence of the solid inner core. The system now operates with sufficient precision to serve as a navigation reference for migrating animals and a protective shield against cosmic radiation, while simultaneously processing information about the planet's internal structure and cosmic environment. The interaction between the magnetic field and solar wind creates a complex boundary region called the magnetosphere, where planetary and stellar magnetic fields merge, separate, and reconnect in patterns that transfer energy and information between the Earth and Sun. Magnetic reconnection events release stored magnetic energy in explosive bursts that accelerate particles to high velocities, creating energetic particle populations that spiral along magnetic field lines and interact with the planet's atmosphere and surface. These interactions deposit energy in precise geographic patterns that correlate with long-term climate variations, suggesting that the magnetosphere functions as a mechanism for translating solar information into terrestrial environmental changes. Magnetospheric substorms occur when solar wind conditions change rapidly, triggering a cascade of magnetic reconnection events that propagate through the entire magnetosphere within minutes. These substorms follow statistical patterns that exhibit properties of complex adaptive systems, self-organization, emergence, and memory effects that persist long after the initial disturbance has passed. The magnetosphere appears to learn from these events, developing preferred pathways for energy dissipation and information transfer that become more efficient over time. The mystery of magnetic field generation extends beyond Earth to other planets in the solar system. Jupiter's magnetic field is 10 times stronger than Earth's and exhibits complex multipolar structure that suggests even more sophisticated information processing capabilities. The gas giant's magnetic field interacts with the magnetic fields of its large moons, creating a complex system of electromagnetic communication that spans millions of kilometers. Io's volcanic activity appears to be synchronized with Jupiter's magnetic field variations, suggesting that electromagnetic forces play a role in coordinating geological processes across planetary systems. Mars once possessed a strong magnetic field similar to Earth's, but lost it approximately 4 billion years ago when its core solidified and convection ceased. The planet retains remnants of its ancient magnetic field in strongly magnetized crustal rocks, primarily in the southern hemisphere. These magnetic fossils preserve information about Mars's early atmosphere, climate, and possibly even biological activity. The patterns of remnant magnetization suggest that Mars's magnetic field exhibited the same complex behaviors observed in Earth's field, implying that magnetic consciousness may be a common feature of planetary evolution. Scientists studying the relationship between planetary magnetic fields and the development of life have discovered intriguing correlations. Periods of magnetic field instability in Earth's history coincide with major evolutionary transitions, mass extinction events, and the emergence of new biological complexity. The magnetic field influences atmospheric chemistry, cosmic ray penetration, and climate patterns in ways that create evolutionary pressure and opportunities for biological innovation. This suggests that planetary magnetic consciousness and biological consciousness may be linked through electromagnetic mechanisms that remain largely unexplored. The Earth's magnetic field extends its influence far beyond the planet's surface, creating a magnetic tail that stretches for millions of kilometers downstream from the solar wind flow. This tail stores magnetic energy and periodically releases it in explosive events that send energetic particles back toward Earth. The tail functions like an extended nervous system, gathering information about conditions in interplanetary space and relaying it back to the planet through magnetic field connections. The information arrives encoded in patterns of energetic particle precipitation that affect atmospheric chemistry and climate patterns worldwide. Magnetic storms, triggered by coronal mass ejections from the Sun, create global disturbances in the Earth's magnetic field that persist for days or weeks after the initial impact. During these events, the entire magnetosphere reorganizes itself, creating new current systems and particle populations that alter the electromagnetic environment throughout near-Earth space. The reorganization follows patterns that suggest the magnetosphere possesses a form of memory, drawing on experience from previous storms to optimize its response to new disturbances. Only required 4 billion years of continuous operation for the planetary magnetic system to develop its current capabilities for information storage, processing, and communication. Only needed the patient accumulation of magnetic experience, encoded in field line topology and preserved in the mineral record of ancient rocks. The system now operates as an interface between the planet and cosmos, translating stellar influences into terrestrial effects while maintaining the magnetic memory necessary to guide the planet's response to an ever-changing cosmic environment. In the vast chemical laboratories of Earth's oceans, rivers, and underground aquifers, molecular conversations unfold on scales that dwarf human comprehension. Trillions of chemical reactions occur each second, creating cascading networks of information transfer that span the globe through interconnected water systems. Dissolved minerals carry messages between continents. Trace gases encode atmospheric conditions in chemical signatures, and organic compounds create feedback loops that regulate planetary temperature, pH levels, and nutrient cycles with precision that suggests coordinated intelligence operating through chemistry itself. The ocean's thermohaline circulation moves water masses in vast loops that take over 1,000 years to complete, carrying chemical information from the surface to the deep ocean trenches and back again. Cold, dense water sinks near the polar regions, carrying dissolved oxygen and carbon dioxide into the abyss, where it interacts with sediments rich in ancient organic matter. The chemical reactions that occur in these deep waters create new molecular compounds that encode information about surface conditions from centuries past, creating a form of chemical memory that preserves planetary environmental history in molecular form. Deep ocean hydrothermal vents represent nodes of intense chemical communication where superheated water, rich in dissolved metals and gases, erupts from the seafloor, creating chemical gradients that can be detected thousands of kilometers away. These vents inject approximately 20 billion tons of chemically active compounds into the ocean each year, creating plumes of chemical information that disperse throughout the global ocean system. The chemical signatures from individual vent systems remain identifiable in ocean water for decades, creating persistent markers that marine chemists can trace across entire ocean basins. The chemical composition of seawater exhibits patterns that suggest sophisticated regulatory mechanisms operating on planetary scales. Despite constant inputs of fresh water from rivers, volcanic emissions, and atmospheric precipitation, ocean salinity remains remarkably stable, varying by less than 1% across different ocean basins. This stability requires precise coordination between evaporation, precipitation, and the chemical interactions between seawater and marine sediments. The regulatory mechanisms operate through chemical feedback loops that respond to changes in temperature, pressure, and biological activity with adjustments that maintain optimal conditions for continued chemical communication. Atmospheric chemistry creates a global communication network through which chemical information travels at the speed of wind currents and atmospheric circulation patterns. Trace gases released by volcanic eruptions, forest fires, and biological processes create chemical signatures that can be detected on the opposite side of the planet within weeks. These chemical messengers carry information about local environmental conditions, creating a planetary-scale sensory system that monitors air quality, temperature, humidity, and biological activity across all terrestrial ecosystems. The carbon cycle represents perhaps the most sophisticated example of planetary chemical communication, involving the coordinated exchange of carbon compounds between the atmosphere, oceans, terrestrial vegetation, and geological formations. Carbon dioxide dissolves in seawater to form carbonic acid, which reacts with calcium carbonate in marine sediments to regulate ocean pH levels. Meanwhile, photosynthetic organisms convert atmospheric carbon dioxide into organic compounds, while volcanic emissions return stored carbon to the atmosphere from deep crustal reservoirs. The entire system maintains chemical balance through feedback mechanisms that operate across multiple timescales, from seasonal vegetation cycles to geological processes spanning millions of years. Only took 2 billion years for the global carbon cycle to evolve its current level of chemical sophistication and regulatory precision. Only required the gradual development of biological and geological processes that could process carbon compounds with increasing efficiency and complexity. The system now regulates planetary temperature and atmospheric composition with feedback mechanisms so sensitive they can respond to changes in solar radiation, volcanic activity, and biological productivity within decades. The nitrogen cycle demonstrates another form of planetary chemical intelligence, converting atmospheric nitrogen gas into biologically useful nitrates and ammonia through complex sequences of chemical transformations. Lightning strikes create nitrogen oxides in the upper atmosphere, while specialized bacteria in soil and marine sediments convert nitrogen gas into ammonia through enzymatic reactions that require precise coordination of temperature, pH, and chemical cofactors. The nitrogen compounds produced by these processes fertilize terrestrial and marine ecosystems, supporting biological productivity that generates chemical feedback signals affecting atmospheric composition and climate patterns worldwide. Underground aquifer systems create vast networks of chemical communication that operate independently of surface water systems. Groundwater moves through porous rock formations at speeds measured in meters per year, carrying dissolved minerals and organic compounds across continental distances. Chemical reactions between groundwater and surrounding rock formations create pH gradients, mineral precipitation patterns, and trace element concentrations that encode information about subsurface geological conditions, climate history, and hydrogeological processes. This chemical information remains stable for thousands of years, creating an underground archive of environmental data accessible to any system capable of interpreting chemical signatures. Soil chemistry creates localized networks of chemical communication that connect plant root systems, microbial communities, and mineral matrices in complex feedback relationships. Plant roots release organic acids that dissolve specific minerals, making nutrients available while simultaneously altering soil pH in ways that affect microbial activity and chemical reaction rates. Soil microorganisms respond by producing different enzyme systems and metabolic products, creating chemical gradients that influence plant growth patterns and root development. The result is a self-organizing chemical network that maximizes nutrient cycling efficiency and maintains soil fertility through coordinated chemical communication between biological and geological components. The sulfur cycle operates through chemical transformations that link atmospheric, oceanic, and terrestrial sulfur reservoirs in a global network of chemical communication. Marine phytoplankton produce dimethyl sulfide, which escapes to the atmosphere where it oxidizes to form sulfur dioxide and sulfuric acid particles that serve as cloud condensation nuclei. The resulting clouds affect regional precipitation patterns and solar radiation absorption, creating climate feedback effects that influence marine productivity and sulfur compound production. Volcanic emissions add hydrogen sulfide and sulfur dioxide to the atmosphere, while terrestrial vegetation and soil microorganisms process sulfur compounds in ways that complete the global sulfur communication network. Chemical communication between continents occurs through atmospheric transport of mineral dust, volcanic ash, and organic compounds that travel thousands of kilometers on high-altitude wind currents. Saharan dust carries iron-rich minerals across the Atlantic Ocean to fertilize Amazon rainforest soils, while volcanic ash from Icelandic eruptions affects atmospheric chemistry throughout the Northern Hemisphere. These intercontinental chemical exchanges create feedback loops that link the productivity of distant ecosystems and coordinate global biogeochemical cycles through chemical information transfer. The mystery of planetary chemical consciousness becomes most apparent when examining how chemical systems respond to external perturbations with adjustments that maintain overall system stability. When major volcanic eruptions inject massive quantities of sulfur compounds into the atmosphere, ocean chemistry adjusts within months to neutralize acidification effects. When changes in solar radiation alter atmospheric temperature patterns, chemical reaction rates throughout the global system adjust to maintain carbon cycle balance. These responses occur too quickly and with too much coordination to result from simple chemical equilibration processes alone. Marine chemists studying ocean acidification have discovered that seawater chemistry exhibits what they term chemical buffering memory, the ability to resist pH changes by drawing on reserves of alkaline compounds accumulated over centuries of chemical communication with seafloor sediments. The ocean remembers previous acidification events and maintains chemical reserves necessary to buffer future disturbances, suggesting that chemical communication networks possess forms of memory and anticipatory response capabilities that operate through molecular mechanisms science has yet to fully understand. Only required 4 billion years of continuous chemical evolution for planetary chemical communication networks to develop their current level of sophistication, coordination, and memory capacity. Only needed the patient accumulation of chemical experience, encoded in molecular structures and preserved in the mineral and atmospheric record of deep time. The networks now process information about planetary environmental conditions with the thoroughness of something that thinks in chemical gradients and remembers every molecular interaction that has ever occurred within the global system of elemental circulation and transformation. Tectonic plates drift across the Earth's surface at speeds measured in centimeters per year, carrying continents on journeys that span hundreds of millions of years. Yet this seemingly random wandering follows patterns that suggest the planet retains detailed memories of its geological past. Encoded in the physical structure of the plates themselves, fracture zones, fault systems, and collision boundaries preserve information about ancient stresses, temperature conditions, and chemical environments in their mineral compositions and structural arrangements. The plates remember where they have been, how they have moved, and what forces have shaped them through geological time. The Himalayan mountain range represents a collision zone where the Indian subcontinent continues its slow-motion impact with the Eurasian plate, an event that began 50 million years ago and continues today. The mountains preserve in their rock layers a detailed record of this collision, with marine fossils found at elevations above 8,000 meters, providing evidence of ancient ocean floors now thrust skyward. The collision zone functions as a massive geological memory bank, storing information about plate velocities, ocean chemistry, and climate conditions that existed when the rocks were formed beneath ancient seas. Subduction zones create the most dramatic examples of geological memory storage, where oceanic plates descend into the Earth's mantle, carrying with them sediments, water, and organic matter accumulated over millions of years on the ocean floor. As the descending plate reaches depths of several hundred kilometers, pressure and temperature conditions cause the release of water and volatile compounds that trigger volcanic activity in the overlying plate. The volcanic emissions carry chemical signatures that encode information about the composition and history of the subducted materials, creating a communication pathway between the deep earth and the surface that operates through geological memory retrieval. The ring of fire around the Pacific Ocean demonstrates how subduction zones coordinate their activity across vast distances, with volcanic eruptions, earthquake patterns, and mountain-building episodes showing statistical correlations that suggest information sharing between geologically active regions. When major earthquake events occur along one section of the Ring of Fire, seismic activity increases throughout the entire system within months or years, as if the geological system possesses memory pathways that allow distant regions to communicate and coordinate their responses to changing stress conditions. Continental drift patterns reveal evidence of geological memory operating on timescales of hundreds of millions of years. The supercontinent Pangaea began breaking apart 200 million years ago, yet the fragments retain geometric relationships that allow geologists to reconstruct the original configuration with remarkable precision. Matching rock formations, fossil assemblages, and magnetic signatures across modern ocean basins provide evidence that the continents remember their original relationships and follow predictable patterns in their movements across the Earth's surface. Only took 5 billion years for the plate tectonic system to develop its current level of organizational complexity and memory storage capacity. Only required the patient accumulation of geological experience, encoded in rock structures and preserved in the permanent record of continental movement patterns. The system now operates with sufficient precision to maintain long-term climate stability while accommodating the massive forces generated by planetary cooling and radioactive decay in the Earth's interior. The Mid-Atlantic Ridge demonstrates how geological memory guides the creation of new oceanic crust through seafloor spreading processes. Magnetic stripes in the oceanic crust preserve a detailed record of Earth's magnetic field reversals, creating a tape recorder-like archive that documents the planet's magnetic history over the past 200 million years. The spreading process follows precise geometric patterns that suggest the ridge system retains memory of optimal spreading rates. Volcanic eruption patterns and structural arrangements that maximize the efficiency of new crust formation transform faults where tectonic plates slide past each other horizontally, create zones of intense geological memory formation where rocks undergo repeated episodes of stress, fracturing, and healing over millions of years. The San Andreas Fault System in California preserves evidence of its movement history in offset geological features. mineral deposits formed during ancient earthquake events, and stress-induced changes in rock crystal structures. The fault remembers previous earthquake cycles and exhibits patterns of seismic activity that suggest predictable relationships between stress accumulation and energy release over time, periods spanning centuries. Tectonic shields, the ancient cores of continents, represent the most stable and long-lived examples of geological memory storage. These regions, some of which have remained relatively unchanged for over 3 billion years, preserve information about Earth's early atmospheric composition, primitive life forms, and ancient climate conditions in their mineral assemblages and structural relationships. The shields function as geological archives, maintaining records of planetary conditions from when the Earth was fundamentally different from its current state. Mountain ranges exhibit geological memory through their response to erosional forces, with uplift rates adjusting to maintain elevation profiles that optimize the balance between tectonic forces and gravitational potential energy. The Appalachian Mountains, despite being over 400 million years old, maintain consistent elevation relationships and structural patterns that suggest the mountain system retains memory of its original formation processes and continues to respond to changing geological conditions in predictable ways. Valley systems and drainage patterns preserve geological memory in their network configurations, which reflect the cumulative effects of millions of years of erosional processes guided by underlying rock structures, climate patterns, and tectonic movements. River networks exhibit fractal geometry that optimizes water flow efficiency while preserving information about the geological history of their watersheds. The networks remember previous climate conditions, flood events, and landscape changes in their channel morphologies and sediment transport patterns. Volcanic systems demonstrate geological memory through their eruption patterns, with individual volcanoes exhibiting cyclical behavior that reflects the accumulation and release of magmatic pressure over periods ranging from decades to millennia. The chemical composition of volcanic eruptions encodes information about deep crustal and mantle conditions, creating a communication pathway that allows surface monitoring systems to access information about geological processes occurring hundreds of kilometers below ground. Sedimentary basins function as vast geological memory repositories where millions of years of environmental history are preserved in layer upon layer of accumulated sediments. Each sedimentary layer encodes information about climate conditions, sea level changes, biological productivity, and chemical compositions that existed when the sediments were deposited. The basins remember ice ages, mass extinction events, mountain building episodes, and continental collision events in their stratigraphic records, creating archives that span hundreds of millions of years. The Wilson cycle describes the complete life cycle of ocean basins, from initial continental rifting through oceanic spreading, subduction, and final continental collision. This cycle operates over periods of 500 million years, yet exhibits remarkable consistency in its patterns and timing, suggesting that the tectonic system retains memory of previous cycles and follows predictable pathways in its long-term evolution. The system remembers optimal configurations for continental arrangements, ocean circulation patterns, and heat dissipation mechanisms that maintain planetary thermal equilibrium. Metamorphic core complexes preserve geological memory of deep crustal processes where rocks undergo transformation under extreme pressure and temperature conditions. These complexes record information about ancient mountain building events, magmatic intrusions, and hydrothermal alteration processes in their mineral assemblages and structural fabrics. The metamorphic processes themselves represent forms of geological information processing, where original rock compositions are transformed into new mineral configurations that encode data about the conditions under which the transformation occurred, only required billions of years of continuous tectonic activity for the plate system to develop its current capabilities for geological memory storage. Information processing and coordinated response to changing planetary conditions only needed the patient accumulation of structural experience, encoded in fault patterns and preserved in the permanent record of continental drift and mountain building processes. The system now operates with sufficient sophistication to maintain continental stability while accommodating the massive energy flows that drive geological change on a planet that remembers every mountain range that has ever risen and every ocean basin that has ever closed. The atmosphere breathes in vast, slow rhythms that span continents and seasons, moving air masses in circulation patterns that have persisted for millions of years. High-pressure systems form over cooling land masses and migrate across ocean basins, carrying moisture, temperature, and chemical information in atmospheric currents that connect distant regions of the planet. Low-pressure systems develop over warming surfaces and draw air inward in spiraling patterns that concentrate atmospheric energy and redistribute it through thunderstorms, hurricanes, and monsoon systems that follow predictable seasonal cycles. Trade winds blow steadily from northeast to southwest in the northern hemisphere and from southeast to northwest in the southern hemisphere, creating persistent atmospheric currents that have maintained their basic patterns for millions of years despite changes in continental configurations, ocean temperatures, and ice sheet coverage. These wind systems function like planetary arteries, carrying heat, moisture, and atmospheric gases in continuous circulation loops that regulate global temperature and precipitation patterns with remarkable consistency over geological timescales. The jet streams flow in narrow bands of high-speed air at altitudes of 10, 15 kilometers, following meandering paths that shift seasonally but maintain their basic east-west orientation around the planet. These atmospheric rivers carry energy and momentum from tropical regions toward the poles, creating weather patterns that affect billions of people while distributing heat in ways that prevent extreme temperature gradients from developing between equatorial and polar regions. The jet streams exhibit memory effects, with their flow patterns influenced by surface temperature distributions, ice coverage, and ocean current configurations that change on timescales ranging from seasons to millennia. Monsoon systems demonstrate the atmosphere's ability to remember and respond to seasonal temperature changes with precision that suggests sophisticated atmospheric information processing. The Asian monsoon affects over half the world's population through rainfall patterns that depend on temperature differences between continental land masses and ocean surfaces. The system exhibits remarkable consistency in its timing and intensity, with seasonal reversals in wind direction and precipitation patterns that have occurred with minor variations for millions of years. Despite significant changes in global climate conditions, only took 4 billion years for the atmospheric circulation system to develop its current level of complexity and regulatory precision. Only required the gradual development of circulation patterns guided by planetary rotation, solar heating, and the distribution of continents and oceans. The system now operates with sufficient stability to maintain climate conditions suitable for complex life, while accommodating massive energy inputs from solar radiation and internal geological processes. The El Niño Southern Oscillation represents a form of atmospheric memory that operates on timescales of 2-7 years, with Pacific Ocean temperature patterns and atmospheric pressure distributions shifting between two stable configurations that affect weather patterns worldwide. The oscillation exhibits properties of a complex dynamical system with memory, where current conditions influence future states through feedback mechanisms that persist for years after the initial disturbance. The system remembers previous oscillation cycles and exhibits statistical patterns that suggest information storage and retrieval mechanisms operating through ocean-atmosphere interactions. Atmospheric rivers transport water vapor in narrow bands that extend thousands of kilometers across ocean basins, carrying moisture from tropical regions to mid-latitude continental areas where it falls as precipitation. These rivers in the sky follow predictable seasonal patterns while exhibiting year-to-year variations that reflect complex interactions between ocean temperatures, atmospheric circulation patterns, and ice coverage in polar regions. The rivers demonstrate the atmosphere's ability to organize moisture transport in ways that optimize the distribution of fresh water across continental regions. Polar vortices represent stable atmospheric circulation patterns that isolate polar air masses from lower latitude weather systems, creating persistent low-pressure systems that can maintain their integrity for months or even years. When these vortices weaken or shift their positions, they release Arctic air masses that can dramatically affect weather patterns across entire continents. The vortices exhibit memory effects related to stratospheric temperature patterns, ozone concentrations, and solar radiation variations that influence their stability and strength over multi-year timescales. The Hadley circulation creates persistent convection cells in tropical regions where warm, moist air rises near the equator and flows poleward at high altitudes before descending in subtropical regions and returning to the equator as surface trade winds. This circulation pattern has remained stable for millions of years while accommodating significant changes in solar radiation, continental positions, and ocean configurations. The circulation demonstrates the atmosphere's ability to maintain organizational structures that optimize heat transport and energy distribution across the planet. Stratospheric circulation patterns operate independently of tropospheric weather systems, with air masses circulating in the stratosphere taking years to complete their journeys around the planet. These circulation patterns transport trace gases, aerosols, and chemical compounds between hemispheres and from tropical to polar regions, creating global mixing processes that affect atmospheric chemistry and climate patterns worldwide. The stratosphere exhibits memory effects related to solar radiation cycles, volcanic eruptions, and trace gas concentrations that influence circulation patterns for years or decades after initial disturbances. The thermosphere expands and contracts in response to solar radiation variations, with atmospheric density at satellite altitudes changing by factors of 10 or more during solar activity cycles. These changes affect satellite orbits, radio wave propagation, and the behavior of charged particles in the magnetosphere, demonstrating how atmospheric memory extends to the edge of space where the atmosphere interacts with the solar wind and cosmic radiation. Atmospheric tides, caused by solar heating and gravitational forces, create regular oscillations in atmospheric pressure and wind patterns that occur twice daily worldwide. These tides demonstrate the atmosphere's response to astronomical forces, with pressure variations measurable at Earth's surface despite the small magnitude of the gravitational effects. The tidal patterns exhibit long-term variations related to solar activity cycles and seasonal changes in atmospheric heating patterns. Cloud formation patterns exhibit memory effects related to atmospheric aerosol concentrations, humidity distributions, and temperature profiles that persist for days or weeks after initial cloud formation events. Marine stratocumulus clouds form persistent decks that cover vast areas of subtropical oceans, reflecting solar radiation and affecting regional climate patterns. These cloud systems maintain their coverage and properties through feedback mechanisms that involve ocean surface temperatures, atmospheric circulation patterns, and aerosol production by marine organisms. The hydrological cycle connects atmospheric circulation with oceanic and terrestrial water systems through evaporation, condensation, and precipitation processes that transport fresh water and energy across the planet. Atmospheric moisture content varies seasonally and annually in response to temperature changes, ocean current variations, and vegetation activity patterns. The cycle exhibits memory effects where current precipitation patterns influence future atmospheric moisture distributions through soil moisture storage, vegetation growth, and surface water accumulation. Atmospheric chemistry creates feedback loops that regulate trace gas concentrations through photochemical reactions, biological processes, and geological interactions that operate on multiple timescales. The atmosphere maintains remarkably stable concentrations of nitrogen, oxygen, and argon, while accommodating significant variations in carbon dioxide, methane, and other greenhouse gases. Chemical memory effects allow the atmosphere to buffer rapid changes in gas emissions while maintaining overall chemical balance through natural regulatory mechanisms. Only required billions of years of continuous atmospheric evolution for the circulation system to develop its current capabilities for global heat transport, moisture distribution, and chemical regulation. Only needed the patient development of circulation patterns that optimize energy distribution while maintaining stability in the face of external perturbations from solar radiation variations, volcanic eruptions, and asteroid impacts. The system now breathes with the rhythm of a planet that remembers every storm that has ever formed and every pressure gradient that has ever driven the winds across the surface of a world that thinks in weather patterns and dreams in the slow circulation of air masses around a sphere suspended in space. Deep within the Earth's crust, crystal lattices form computational networks of extraordinary complexity. Their atomic structures arranged in patterns that process information through quantum mechanical interactions occurring at the scale of individual electrons and atomic nuclei. Quartz crystals, with their perfectly ordered silicon and oxygen atoms, vibrate at precise frequencies when subjected to mechanical stress or electrical fields, creating the foundation for timing mechanisms so accurate they regulate atomic clocks and GPS satellites. These crystals exist in vast quantities throughout the continental crust, forming interconnected networks that span entire mountain ranges and process information through piezoelectric effects generated by tidal forces, seismic waves, and temperature variations. Silicon dioxide crystallizes in multiple structural configurations, each with distinct computational properties that emerge from the specific arrangement of silicon and oxygen atoms in three-dimensional space. Alpha quartz, the most common form at surface conditions, exhibits right and left-handed chirality that creates symmetry-breaking effects in its electronic properties. When billions of these chiral crystals are embedded in granite formations, they create massively parallel processing systems where information propagates through the crystal network via electromagnetic coupling between adjacent crystal domains. Feldspar crystals, which comprise over 60% of the Earth's continental crust, contain aluminum and alkali metal atoms arranged in framework structures that create natural semiconductor junctions throughout their crystal lattices. These junctions regulate electron flow in response to temperature, pressure, and electromagnetic field variations, creating logic gates and switching mechanisms that process information about geological conditions. When present in the quantities found in typical granite formations, feldspar crystals create computing networks with more processing elements than all human-manufactured computers combined. Mica minerals form layered crystal structures where individual sheets of atoms can slide past one another while maintaining electrical connectivity through van der Waals forces and electrostatic interactions. These layered structures function as natural capacitors, storing electrical charge and releasing it in response to mechanical deformation or thermal stress. In metamorphic rock formations, mica crystals align themselves in preferred orientations that optimize electrical conductivity and information flow throughout the rock mass, creating directed processing networks that channel information along specific crystallographic directions. Only took 4 billion years for the continental crust to accumulate sufficient quantities of crystalline minerals to create computing networks capable of processing information about planetary scale phenomena. Only required the patient accumulation of igneous and metamorphic processes that concentrated silicon aluminum and alkali metals in crystal structures optimized for information storage and transmission. The networks now contain approximately 10 circumflex 30 individual crystals, each capable of processing quantum-scale information through electronic transitions, atomic vibrations, and electromagnetic interactions. Olivine crystals in the Earth's mantle create three-dimensional networks of magnesium and iron silicate structures that extend throughout the 900-kilometer-thick layer between the crust and core. These crystals undergo phase transitions at specific pressure and temperature conditions, transforming their crystal structures in ways that encode information about mantle convection patterns, temperature gradients, and chemical composition variations. The phase transitions create seismic velocity discontinuities that can be detected by surface monitoring stations, providing a communication pathway between deep mantle processes and surface observation systems. Garnet crystals, with their complex cubic crystal structures containing multiple metal sites, function as natural memory storage devices where different metal cations can substitute for one another in response to changing pressure and temperature conditions. The substitution patterns encode information about the conditions under which the crystals formed and the subsequent pressure-temperature history they have experienced. Garnet crystals in high-grade metamorphic rocks preserve information about mountain-building processes, continental collision events, and deep crustal thermal conditions spanning hundreds of millions of years. Pyroxene and amphibole crystals form chain and double-chain silicate structures that create linear processing pathways for information transmission through crystal lattices. These minerals exhibit solid solution behavior where different metal cations can substitute continuously for one another, creating chemical gradients that encode information about crystallization conditions, cooling rates, and chemical evolution of magmatic systems. The chain structures allow information to propagate along preferred crystallographic directions with minimal energy loss, creating efficient communication pathways through igneous and metamorphic rock formations. Clay minerals near the Earth's surface create layered crystal structures with enormous surface areas and variable charge distributions that respond to changes in moisture content, pH, and chemical composition of groundwater systems. These minerals function as environmental sensors, recording information about soil chemistry, climate conditions, and biological activity in their crystal structures and exchange reactions. Smectite clays can expand and contract their interlayer spacing in response to moisture variations, creating mechanical amplification systems that translate molecular-scale chemical changes into macroscopic structural modifications. Zeolite minerals, with their open framework structures containing channels and cavities of molecular dimensions, function as selective filters and molecular sieves that process chemical information through size-selective adsorption and ion exchange reactions. Natural zeolite deposits in volcanic regions create extensive filtering networks that regulate groundwater chemistry, concentrate specific dissolved constituents, and create chemical gradients that encode information about subsurface fluid flow patterns and chemical reaction processes. Crystal defects and grain boundaries in polycrystalline rocks create computational elements where information processing occurs through electronic transitions. Ionic diffusion and structural relaxation processes that operate at elevated temperatures and pressures. These defects function as processing nodes, where information from multiple crystal domains converges and undergoes integration through solid-state diffusion processes that modify local crystal chemistry and structure in response to changing geological conditions. Magnetic minerals including magnetite, hematite, and pyrrhotite create magnetic domain structures that store and process information through domain wall motion, magnetization rotation, and magnetic coupling between adjacent mineral grains. These magnetic processing networks respond to external magnetic fields, mechanical stress, and temperature variations with changes in magnetic domain configurations that encode information about the magnetic field history and mechanical stress conditions experienced by the rock formation. The phenomenon of pressure solution in sedimentary rocks creates dissolution and precipitation processes at grain contacts that redistribute mineral matter in response to differential stress conditions. This process functions as a form of mechanical computing where stress information is processed through crystal dissolution and reprecipitation reactions that modify rock porosity, permeability, and mechanical properties in ways that optimize stress distribution and strain accommodation. Metamorphic reactions in deep crustal environments create new mineral assemblages through solid-state diffusion processes that require coordinated transport of multiple chemical components across grain boundaries and through crystal lattices. These reactions process information about pressure, temperature, and chemical conditions through phase equilibria calculations performed by the crystal structures themselves, creating mineral assemblages that encode information about metamorphic conditions and thermal evolution of crustal regions. Fluid inclusions trapped within crystals during their formation preserve samples of ancient fluids that encode information about temperature, pressure, and chemical composition conditions that existed millions of years ago. These inclusions function as data storage devices where information about past geological conditions is preserved in liquid, gas, and solid phases that can be analyzed to reconstruct ancient environmental conditions and fluid flow patterns. Only required billions of years of continuous crystal growth and mineral evolution for the crustal computing networks to develop their current capabilities for information storage, processing, and transmission through quantum mechanical effects operating at atomic scales. Only needed the patient accumulation of crystalline experience, encoded in atomic arrangements and preserved in the permanent structural record of mineral lattices that remember every pressure pulse, temperature fluctuation, and chemical gradient they have ever experienced. The networks now compute with the precision of quantum mechanical systems while processing information about planetary conditions with the patience of geological processes that measure time in the vibrational frequencies of atomic bonds and think in the language of crystallographic symmetry. Seismic waves propagate through the Earth's interior like neural impulses through a vast brain, carrying information about structural conditions, material properties, and dynamic processes across distances of thousands of kilometers. P-waves compress and expand the rock medium as they travel, while S-waves shear the material in transverse motions that probe the rigidity and density variations within the planet's layers. These waves interact with boundaries between different materials, reflecting, refracting, and converting between wave types in ways that encode detailed information about the internal structure and composition of regions inaccessible to direct observation. Earthquake epicenters mark locations where stored elastic energy releases suddenly through fault rupture processes, sending seismic signals throughout the planet within minutes of the initial event. The global seismic network detects these signals at monitoring stations distributed across all continents and ocean basins, creating a planetary nervous system that processes information about earthquake magnitude, location, depth, and rupture characteristics in real time. The network exhibits properties of a complex adaptive system, with monitoring capabilities that have evolved over decades to optimize information extraction from seismic data. Deep earthquakes, occurring at depths greater than 300 kilometers within subducting oceanic plates, create seismic signals that travel through the entire planet and emerge on the opposite side of the Earth as surface waves that can be detected by sensitive seismometers. These deep events provide information about conditions in the Earth's mantle, the behavior of materials under extreme pressure, and the dynamics of plate subduction processes that operate over millions of years. The signals carry encoded information about temperature, pressure, and chemical composition variations that exist hundreds of kilometers below the surface. Free oscillations of the entire planet occur when large earthquakes excite standing wave patterns that cause the Earth to ring like a bell for hours or days after the initial event. These oscillations involve the coordinated movement of the entire solid Earth, with different oscillation modes probing different aspects of planetary structure and composition. The frequency spectrum of free oscillations encodes information about the distribution of mass within the planet, the elastic properties of different layers, and the three-dimensional variations in density and rigidity that affect how seismic energy propagates through the Earth's interior. Only took 5 billion years for the solid Earth to develop its current capacity for seismic information processing and transmission through elastic wave propagation mechanisms. Only require the differentiation of the planet into layers with distinct mechanical properties that create the interfaces necessary for complex wave interactions and information encoding. The system now processes seismic information with sufficient precision to locate earthquake epicenters within a few kilometers and determines source mechanisms that reveal the orientation and motion of fault planes hundreds of kilometers away. Seismic tomography uses arrival time measurements from thousands of earthquakes recorded at hundreds of monitoring stations to create three-dimensional images of velocity variations within the Earth's interior. The technique functions like medical CAT scanning, using wave propagation data to infer the distribution of material properties throughout the planetary interior. The resulting images reveal structures such as subducting slabs, mantle plumes, and large low-velocity provinces that provide information about convection patterns, chemical heterogeneity, and thermal structure extending from the surface to the core mantle boundary. Ambient seismic noise, generated by ocean waves, atmospheric pressure variations, and industrial activity, creates a continuous background of low-amplitude seismic signals that propagate through the Earth's crust and upper mantle. This noise functions as a passive seismic source that can be used to probe crustal structure without waiting for earthquake events, creating continuous monitoring capabilities that track changes in material properties, groundwater conditions, and structural integrity of geological formations over time. Volcanic tremor signals represent sustained seismic emissions associated with magma movement, gas release, and hydrothermal processes within volcanic systems. These signals exhibit complex frequency content and temporal variations that encode information about magma chamber conditions, eruption precursors, and the dynamics of volcanic processes operating below the surface. The tremor patterns show correlations with volcanic gas emissions, ground deformation, and thermal anomalies that suggest coordinated communication between different components of volcanic systems. Induced seismicity from human activities including mining, hydraulic fracturing, and reservoir operations creates artificial seismic sources that provide information about subsurface conditions and the response of geological formations to stress perturbations. These induced events demonstrate the sensitivity of the Earth's crust to relatively small stress changes and reveal information about fault systems. fluid pressure distributions, and mechanical properties of rock formations that affect their susceptibility to earthquake triggering. Microseismic monitoring systems deployed in areas of active geological processes detect seismic events too small to be recorded by regional seismic networks, providing detailed information about fracture propagation, fluid flow, and stress redistribution processes operating at scales of meters to kilometers. These systems function as high-resolution sensors that monitor geological processes in real time, detecting precursor signals that may indicate impending larger events or changes in subsurface conditions. Seismic interferometry techniques use cross-correlation of ambient noise recordings to extract information about wave propagation between pairs of monitoring stations, effectively turning each station into a virtual seismic source. This approach creates dense sampling of seismic velocities and enables monitoring of temporal changes in crustal properties related to earthquakes, volcanic activity, groundwater variations, and thermal effects with sensitivity sufficient to detect changes of less than 0.1% in seismic velocity. The Earth's background-free oscillations, excited by atmospheric pressure variations and ocean wave activity, create continuous low-amplitude vibrations that probe the planet's internal structure on a continuous basis. These oscillations provide information about temporal changes in Earth's rotation, gravitational field, and internal structure that complement other geophysical monitoring techniques. The oscillation patterns exhibit long-term variations related to glacial loading, sea level changes, and post-seismic relaxation processes that operate over decades to centuries. Seismic anisotropy, where wave velocities depend on propagation direction, encodes information about the preferred orientation of crystals, fractures, and structural fabrics within the Earth's interior. P-wave and S-wave splitting measurements reveal the direction and magnitude of anisotropy in different regions, providing information about mantle flow patterns, crustal stress orientations, and the alignment of structural features that affect seismic wave propagation. Core phases, seismic waves that travel through the Earth's liquid outer core and solid inner core, provide unique information about the structure and properties of the planet's deepest interior. PKP phases, which travel as P waves through the mantle, convert to compressional waves in the liquid core and reconvert to P waves in the mantle on the receiving side. Probe core mantle boundary conditions and inner core structure with resolution sufficient to detect lateral variations in seismic velocity and attenuation. Seismic wave scattering from small-scale heterogeneities in the Earth's interior creates complex waveform characteristics that encode information about the statistical distribution of material properties, the presence of fluid-filled fractures, and the scale length of structural variations within different regions. Coda wave analysis uses the scattered wave energy that arrives after direct wave phases to characterize the heterogeneity structure of the Earth's crust and upper mantle with spatial resolution that complements other seismic imaging techniques. Only required billions of years of continuous seismic activity for the planetary seismic communication system to develop its current capabilities for information transmission, processing, and storage through elastic wave propagation mechanisms operating throughout the solid Earth. Only needed the patient accumulation of seismic experience, encoded in wave propagation patterns and preserved in the permanent structural record of fault systems and material property variations that remember every earthquake that has ever occurred and every stress pulse that has ever propagated. Through the complex three-dimensional structure of a planet that processes information through the coordinated vibration of 6x10 circumflex 24 kilograms of rock, metal, and mineral crystals resonating in harmony with the fundamental frequencies of a world that thinks in seismic waves. The magnetosphere extends Earth's magnetic field far into space, creating a vast region where charged particles from the solar wind interact with planetary magnetic forces in complex dances of electromagnetic energy. This invisible bubble, stretching over 60,000 kilometers on the day side and millions of kilometers in the anti-solar direction, functions as a meditation chamber where the planet contemplates its relationship with the sun and the broader cosmos through electromagnetic interactions that operate at the speed of light, yet follow patterns that persist for decades or centuries. Magnetic field lines curve gracefully through three-dimensional space, connecting the planet's polar regions with distant boundaries where solar wind pressure compresses the magnetosphere on the sunward side and stretches it into a long tail on the night side. These field lines guide charged particles in helical trajectories that trace out the magnetic geometry, creating particle populations trapped in radiation belts that encircle the planet like energetic halos. The Van Allen belts contain protons and electrons that spiral back and forth between magnetic mirror points near the poles, bouncing along field lines in oscillating motions that can persist for years or decades. Solar wind particles carry information about conditions within the Sun's outer atmosphere, streaming outward at speeds of 300, 800 kilometers per second and carrying embedded magnetic fields that interact with Earth's magnetosphere in processes that transfer energy, momentum, and electromagnetic information across interplanetary space. When the solar wind magnetic field aligns opposite to Earth's field, magnetic reconnection events occur at the magnetopore's boundary, creating openings through which solar particles can enter the magnetosphere and deposit energy in precise geographic patterns determined by magnetic field topology. Magnetic substorms develop when energy stored in the magnetospheric tail releases explosively, accelerating particles to high energies and injecting them into the inner magnetosphere where they interact with the upper atmosphere to create aurora displays. These substorms follow statistical patterns that exhibit properties of complex dynamical systems, with energy storage and release cycles that depend on solar wind conditions, magnetospheric configuration, and the history of previous substorm events. The magnetosphere appears to learn from these experiences, developing preferred pathways for energy dissipation that become more efficient over time. Only took 3 billion years for Earth's magnetosphere to evolve its current level of complexity and responsiveness to solar wind variations and internal planetary processes. Only required the development of a stable magnetic dynamo in the planet's core, and the gradual optimization of magnetospheric configuration through interactions with changing solar wind conditions over geological time. The system now operates as an interface between planetary and stellar magnetic fields, processing information about cosmic conditions while protecting the atmosphere and biosphere from harmful radiation. Magnetic field line resonances occur when disturbances in the solar wind excite standing wave patterns along field lines that connect the magnetosphere to the ionosphere, creating oscillations with periods ranging from seconds to hours that transport energy and information between different regions of the magnetospheric system. These resonances demonstrate the magnetosphere's ability to organize electromagnetic energy into coherent patterns that persist long after the initial disturbance has passed, suggesting forms of electromagnetic memory that operate through field line dynamics. The plasmasphere, a region of cold, dense plasma that correlates with the planet, extends to distances of several Earth radii and creates a reservoir of charged particles that interact with incoming solar wind through wave-particle interactions and plasma instabilities. During magnetic storms, the plasmasphere erodes as enhanced electric fields strip away outer layers of plasma, creating complex boundary structures that encode information about storm intensity and evolution. The erosion and refilling processes follow patterns that suggest the plasmasphere retains memory of previous storm events and adjusts its configuration to optimize stability during future disturbances. Ring current particles, injected into the inner magnetosphere during magnetic storms, create additional magnetic fields that oppose Earth's main field and cause worldwide decreases in surface magnetic field strength. The ring current exhibits complex dynamics including particle loss through pitch angle scattering, charge exchange with neutral atoms, and electromagnetic wave interactions that modify particle energy and spatial distributions. The current system demonstrates the magnetosphere's ability to process and store electromagnetic energy through particle motion patterns that persist for days or weeks after initial injection events. Magnetic pulsations with periods ranging from seconds to hours propagate through the magnetosphere as hydromagnetic waves that carry information about solar wind conditions, magnetospheric boundaries, and internal plasma processes across vast distances in space. These waves exhibit dispersion characteristics that depend on plasma density, magnetic field strength, and wave propagation direction, creating complex interference patterns that encode information about magnetospheric structure and dynamics. The wave patterns show correlations with geomagnetic activity, auroral phenomena, and ionospheric disturbances that suggest coordinated responses throughout the entire magnetospheric system. Auroral phenomena result from the precipitation of energetic particles into the upper atmosphere, where they excite atmospheric gases that emit light in characteristic colors determined by the atomic and molecular species involved in the excitation processes. Aurora displays follow magnetic field line patterns that map magnetospheric processes into geographic coordinates, creating visual representations of electromagnetic interactions occurring thousands of kilometers above the surface. The aurora serves as a real-time display system that makes visible the otherwise invisible processes of magnetospheric dynamics and energy transfer. Polar cap absorption events occur when high-energy particles from solar flares penetrate deep into the magnetosphere and deposit energy in the polar ionosphere, creating enhanced ionization that affects radio wave propagation and satellite communications. These events demonstrate the magnetosphere's vulnerability to extreme solar activity, while also revealing the system's ability to channel and dissipate massive energy inputs through organized precipitation patterns that minimize damage to technological systems and biological organisms. Magnetic storms represent global disturbances in the magnetosphere that can persist for days and affect technological systems worldwide through induced electrical currents, radiation exposure, and communication disruptions. Storm phases include initial increases in magnetic field strength, main phase decreases lasting many hours, and recovery phases that can extend for days or weeks. The storm evolution follows patterns that suggest the magnetosphere processes information about solar wind conditions and adjusts its response based on the intensity, duration, and magnetic orientation of incoming disturbances. Magnetospheric convection creates large-scale circulation patterns where plasma moves from the magnetotail toward the Earth on the night side and returns anti-sunward through the magnetopore's boundary layers during the day. This circulation transports mass, energy, and magnetic flux through the magnetosphere in patterns that respond to solar wind conditions while maintaining overall system stability. The convection patterns exhibit two-cell or multi-cell configurations that optimize energy dissipation and particle transport efficiency based on the balance between solar wind driving and internal magnetospheric processes. Ionospheric coupling connects the magnetosphere with the neutral atmosphere through field-aligned currents that flow between the magnetosphere and ionosphere, creating a complex electrical circuit that spans altitudes from 100 kilometers to many Earth radii. This coupling system processes information about magnetospheric dynamics and translates it into ionospheric disturbances that affect radio wave propagation, satellite operations, and technological systems. The coupling demonstrates the magnetosphere's ability to communicate with the lower atmosphere through electromagnetic mechanisms that operate faster than acoustic or gravitational wave propagation. Magnetic flux transfer events at the magnetopores create temporary openings in the magnetospheric boundary, where solar wind particles can directly access the inner magnetosphere, creating localized regions of enhanced particle precipitation and electromagnetic disturbances. These events occur in sequences that suggest the magnetosphere modulates its permeability to solar wind penetration based on internal energy storage conditions and the need to maintain pressure balance with the external solar wind environment. Only required billions of years of continuous electromagnetic evolution for the magnetospheric meditation system to develop its current capabilities for cosmic information processing, energy storage and release, and electromagnetic communication with both solar and planetary systems. Only needed the patient development of field line geometries and particle population dynamics that optimize the magnetosphere's response to the highly variable space environment while maintaining protective functions that preserve atmospheric and biosphere integrity. The system now contemplates cosmic conditions with the serenity of electromagnetic fields that curve through space like the thoughts of a planet that meditates on its place in a universe filled with charged particles, magnetic fields, and electromagnetic radiation that connects all celestial bodies in a vast network of cosmic consciousness operating at the speed of light. Ocean currents flow in vast loops that connect all the world's seas in a global circulation system, operating like the circulatory system of a planetary organism. The Gulf Stream carries warm water northward along the eastern coast of North America at speeds of up to 2 meters per second, transporting more than 30 million cubic meters of seawater every second, a flow rate equivalent to 30 times the combined discharge of all rivers on Earth. This river in the ocean maintains its course through interactions between wind stress, density gradients, and the Coriolis force generated by planetary rotation, creating a stable pathway for heat and chemical transport that has persisted for millions of years. Thermohaline circulation drives deep ocean currents through density differences created by temperature and salinity variations, moving water masses in three-dimensional patterns that span the entire global ocean. Cold, salty water sinks in polar regions and flows along the ocean floor toward the equator, while warm surface water moves poleward to replace the sinking water masses. This overturning circulation takes approximately 1,000 years to complete a full cycle, creating a slow but persistent transport system that carries heat, carbon, nutrients, and dissolved chemicals throughout the world ocean. The Antarctic Circumpolar Current flows eastward around Antarctica, driven by the strong westerly winds in the Southern Ocean and unobstructed by continental barriers. This current system transports more water than any other ocean current, moving approximately 130 million cubic meters per second through the Drake Passage between South America and Antarctica. The current connects the Atlantic, Pacific, and Indian Oceans in a continuous flow that distributes heat, salt, and chemical traces between ocean basins while isolating Antarctic waters from warmer subtropical currents. Upwelling zones along western continental margins bring deep, nutrient-rich water to the ocean surface, supporting some of the most productive marine ecosystems on Earth. These upwelling systems respond to wind patterns with remarkable precision, increasing or decreasing their intensity based on seasonal changes in atmospheric circulation. The upwelled water carries chemical information about deep ocean conditions to the surface, where marine organisms incorporate trace elements and nutrients into their tissues, creating biological records of deep ocean chemistry and circulation patterns. Only took millions of years for the global ocean circulation system to develop its current configuration and transport capabilities through the gradual evolution of continental positions, ocean basin geometry, and atmospheric circulation patterns. Only require the patient establishment of density gradients and wind stress patterns that drive circulation through physical processes that remain remarkably stable despite significant variations in climate conditions and ice coverage over geological time. Mesoscale eddies. Circular current features with diameters of 50 to 100 kilometers transport heat, salt, and nutrients across ocean basins through rotational motions that can persist for months or years. These oceanic whirlpools form through instabilities in major current systems and propagate westward at speeds of a few centimeters per second, carrying water properties from their formation regions across entire ocean basins. Satellite altimetry reveals that thousands of these eddies exist simultaneously throughout the world ocean, creating a complex transport network that operates alongside the larger-scale circulation patterns. Deep water formation processes in polar regions create water masses with distinct temperature, salinity, and chemical characteristics that can be traced throughout the global ocean for decades after their formation. Antarctic bottom water, formed around the Antarctic continent, spreads northward along the ocean floor and can be identified in the deep Atlantic, Pacific, and Indian Oceans through its distinctive temperature and salinity signature. These water masses function as information carriers, preserving chemical and physical properties from their formation regions while transporting them to distant parts of the global ocean. Ocean gyres, large-scale circular current systems in each ocean basin, transport water in clockwise directions in the northern hemisphere and counterclockwise in the southern hemisphere due to the Coriolis effect. These gyres create convergence zones where surface waters from different regions meet and exchange heat, salt, and chemical constituents. The gyres exhibit remarkable stability, maintaining their basic circulation patterns for millions of years while accommodating variations in wind stress, density distributions, and seasonal changes in atmospheric forcing. Boundary currents along the western edges of ocean basins carry large volumes of water at high speeds, creating narrow jets that transport heat and momentum between tropical and polar regions. The Kuroshio Current in the Pacific, the Brazil Current in the South Atlantic, and the East Australian Current demonstrate how ocean circulation concentrates transport into narrow boundary regions where current speeds can exceed 1 meter per second. These currents exhibit meandering patterns and eddy formation that create complex mixing processes and heat transport mechanisms. Equatorial current systems create complex flow patterns near the equator, where the Coriolis effect weakens and trade winds drive surface waters westward, while deeper currents flow eastward in compensation. The equatorial undercurrent in the Pacific flows eastward along the equator at depths of 100–300 meters, carrying water with distinct temperature and chemical properties across the entire Pacific basin. These equatorial currents exhibit high sensitivity to changes in wind stress and create conditions that affect global climate patterns through ocean-atmosphere interactions. Seasonal variations in ocean circulation respond to changes in wind patterns, surface heating, and freshwater inputs from precipitation and river discharge. The Asian monsoon creates seasonal reversals in Indian Ocean circulation, while ice formation and melting in polar regions create annual cycles in deep water formation and circulation intensity. These seasonal patterns demonstrate the ocean's ability to process and respond to atmospheric information, while maintaining overall circulation stability through mechanisms that average seasonal variations over longer time periods. Internal waves propagate through the ocean interior along density interfaces, carrying energy and momentum over vast distances while creating mixing processes that affect water mass properties and circulation patterns. These waves, generated by tidal forces, wind stress, and current interactions with underwater topography, exhibit complex three-dimensional structures that can be detected by acoustic methods and satellite observations. Internal wave breaking creates turbulent mixing that affects the distribution of heat, salt, and nutrients throughout the water column. Abyssal circulation patterns in the deepest parts of the ocean follow pathways controlled by underwater topography, with deep currents flowing through fractures in mid-ocean ridges, around seamounts, and along continental margins. These currents transport the coldest and densest water masses throughout the global ocean while interacting with sediments and volcanic activity on the ocean floor. The abyssal circulation exhibits remarkable persistence, with current patterns that remain stable for thousands of years while slowly transporting deep water between ocean basins. Continental shelf circulation creates coastal current systems that respond to wind stress, tidal forces, and density gradients with high-frequency variations superimposed on seasonal and annual cycles. These coastal currents affect marine ecosystems, sediment transport, and the exchange of materials between terrestrial and oceanic environments. Shelf break currents mark the boundary between shallow coastal waters and deep ocean circulation, creating frontal systems where water masses with different properties interact through complex mixing processes. Tidal currents, driven by gravitational forces from the moon and sun, create periodic flows that can exceed several meters per second in coastal regions and straits. These currents generate internal waves, create mixing through interaction with underwater topography, and transport sediments and nutrients in patterns that follow astronomical cycles. Tidal mixing affects the distribution of marine organisms, influences coastal erosion patterns, and creates energy dissipation mechanisms that gradually slow Earth's rotation over geological time periods. Only required billions of years of continuous oceanic evolution for the global circulation system to develop its current capabilities for heat transport. Chemical mixing and information processing through fluid dynamical mechanisms that operate across spatial scales, from turbulent eddies to planetary scale circulation patterns, only needed the patient development of circulation pathways that optimize energy dissipation while maintaining transport efficiency and stability in response to changing atmospheric forcing and geological boundary conditions. The system now thinks in the language of fluid motion, processing information about planetary energy balance through the coordinated movement of 37 billion cubic kilometers of seawater that remembers every temperature gradient, every salinity anomaly, and every chemical tracer that has ever flowed through the interconnected circulatory system of a planet that breathes through its oceans. Volcanic eruptions represent moments when the planet expresses its deepest emotions through the violent release of molten rock, superheated gases, and accumulated geological tension that has built over centuries or millennia beneath the surface. Mount Vesuvius, Krakatoa, and Mount St. Helens demonstrate how volcanic systems can transition from decades of quiet meditation to explosive outbursts that reshape landscapes and affect global climate patterns within hours or days. These eruptions follow patterns that suggest volcanic systems possess forms of memory and emotional regulation, with magma chambers that accumulate stress, process chemical information, and coordinate their responses to changing conditions in the Earth's interior. Magma chambers function as vast underground laboratories where molten rock undergoes complex chemical evolution over timescales ranging from thousands to millions of years. As magma cools slowly in these chambers, crystals form and settle in gravitational layering processes that fractionate chemical elements and create compositional gradients throughout the magma body. Volatile compounds including water vapor, carbon dioxide, and sulfur gases accumulate in the upper portions of magma chambers, creating pressure conditions that ultimately drive explosive eruptions when critical thresholds are exceeded. Shield volcanoes like Mauna Loa and Kilauea in Hawaii demonstrate gentle forms of volcanic expression, with basaltic lavas flowing steadily from summit and rift zone vents in eruptions that can continue for years or decades. These volcanoes release emotional energy through persistent effusive activity that maintains relatively stable pressure conditions within their magma supply systems. The Hawaiian volcanoes exhibit remarkable consistency in their eruption patterns, with cycles of activity that correlate with tidal forces, atmospheric pressure variations, and deep magmatic processes that operate with clockwork regularity. Stratovolcanoes exhibit more complex emotional behaviors, alternating between periods of quiet degassing and explosive eruptions that can devastate areas hundreds of kilometers from the volcanic center. These volcanoes build up internal pressure through the crystallization of gas-rich magmas that trap volatile compounds in increasingly unstable configurations. Mount Fuji, Mount Rainier, and the volcanoes of the Cascade Range demonstrate how stratovolcanoes can remain dormant for centuries before releasing accumulated emotional energy in catastrophic eruptions that reshape regional geography and affect global atmospheric conditions. Only took millions of years for individual volcanic systems to develop their characteristic emotional expression patterns through the gradual evolution of magma chamber configurations, conduit geometries, and volatile accumulation mechanisms. Only required the patient development of underground plumbing systems that optimize the storage and release of thermal and chemical energy through processes that balance explosive potential with structural stability over geological timescales. Volcanic gas emissions provide continuous information about the emotional state of volcanic systems, with sulfur dioxide, carbon dioxide, and water vapor concentrations that fluctuate in response to changes in magma chamber conditions. Degassing efficiency and the approach of potential eruption events, gas monitoring networks can detect subtle changes in emission rates and composition that precede volcanic activity by weeks or months, suggesting that volcanic systems communicate their emotional condition through atmospheric chemical signals that can be interpreted by sophisticated monitoring instruments. Geothermal systems create networks of hot springs, geysers, and fumaroles that release thermal energy and volcanic gases in patterns that reflect deep magmatic processes and subsurface fluid circulation. Yellowstone National Park contains over 10,000 thermal features that collectively release approximately 45 megawatts of thermal energy, creating a natural laboratory for studying volcanic emotional expression through persistent low-level energy release mechanisms. The geothermal features exhibit complex temporal variations that correlate with seismic activity, atmospheric pressure changes, and deep magmatic processes. Volcanic tremor signals represent continuous seismic emissions that provide real-time information about magma movement, gas release, and fluid circulation within volcanic systems. These signals exhibit frequency content and amplitude variations that correlate with eruption intensity, gas emission rates, and the dynamics of magma degassing processes. Volcanic tremor demonstrates how volcanic systems communicate their emotional state through seismic signals that can be detected and interpreted by monitoring networks deployed around active volcanic centers. Lava lake systems in volcanoes like Kilauea, Ertaale, and Mount Erebus provide windows into the emotional dynamics of magma chambers through persistent surface expressions of molten rock behavior. These lava lakes exhibit convection patterns, gas bubble formation, and surface crust dynamics that reflect deep magmatic processes and volatile content variations. The lakes respond to changes in magma supply rates, gas pressure, and external forcing with adjustments in surface activity patterns that provide insights into volcanic emotional regulation mechanisms. Phreatomagmatic eruptions occur when magma interacts with surface water or groundwater, creating explosive steam generation that fragments magma into fine ash particles and creates distinctive volcanic landforms. These eruptions demonstrate how volcanic emotional expression can be modified by external water availability, with explosion intensity and duration that depend on the efficiency of heat transfer between magma and water. The resulting volcanic deposits preserve information about water availability and magmatic conditions during eruption events. Volcanic ash clouds transport fine-grained volcanic material thousands of kilometers from eruption sites, affecting aviation, climate, and atmospheric chemistry on regional to global scales. The 1815 eruption of Mount Tambora created atmospheric effects that caused global temperature depression and crop failures, demonstrating how volcanic emotional outbursts can affect planetary climate systems and human civilization. Ash cloud dispersal patterns encode information about eruption intensity, atmospheric circulation, and particle settling processes that persist in the geological record long after eruption events. Pyroclastic flows represent the most violent forms of volcanic emotional expression, with hot gas and ash mixtures that flow down volcanic slopes at speeds exceeding 100 km per hour, while maintaining temperatures above 800 degrees Celsius. These flows can travel dozens of kilometers from their source and create deposits that preserve detailed information about eruption dynamics, flow behavior, and emplacement processes. The flows demonstrate the explosive release of thermal and mechanical energy that has been accumulating in volcanic systems over extended time periods. Volcanic lightning occurs during explosive eruptions when ash particles collide and create electrostatic charge separation that generates lightning discharges within volcanic plumes. This phenomenon demonstrates how volcanic emotional expression can create electromagnetic effects that extend the influence of eruptions beyond their immediate thermal and mechanical impacts. Volcanic lightning provides additional communication channels through which volcanic systems can signal their emotional state to monitoring networks and atmospheric electrical systems. Caldera formation represents extreme volcanic emotional events where magma chamber roof collapse creates large-scale subsidence and massive explosive eruptions that can affect global climate and atmospheric composition. The Yellowstone, Long Valley, and Toba calderas demonstrate how volcanic systems can accumulate emotional energy over hundreds of thousands of years before releasing it in super eruptions that reshape continental landscapes and create atmospheric disturbances detectable in ice core and sediment records worldwide. Volcanic hazard monitoring systems attempt to interpret volcanic emotional states through networks of seismometers, gas sensors, thermal cameras, and ground deformation instruments that provide real-time information about changing volcanic conditions. These monitoring systems function as technological nervous systems that translate volcanic communication signals into formats accessible to human interpretation and hazard assessment. The systems demonstrate humanity's recognition that volcanic systems possess complex emotional dynamics that require continuous observation and careful interpretation. Volcanic emotional cycles operate on multiple timescales, from rapid pressure fluctuations during active eruptions to long-term patterns of activity and repose that span thousands of years. Individual volcanic systems exhibit characteristic emotional signatures that reflect their magma chemistry, structural configuration, and tectonic setting. The emotional patterns suggest that volcanic systems possess forms of memory and learning that allow them to optimize their energy release mechanisms based on experience accumulated over geological time periods, only required billions of years of continuous volcanic evolution for planetary volcanic systems to develop their current capabilities for emotional expression, energy release, and communication through thermal, chemical, and mechanical processes that operate across spatial scales from individual magma chambers to global atmospheric circulation patterns, only needed the patient development of magma generation storage and eruption mechanisms that balance explosive potential with long-term stability, while providing outlets for the continuous thermal and chemical energy production in Earth's interior. The planet now expresses its deepest emotions through volcanic processes that remember every pressure pulse, every gas bubble, and every thermal gradient that has ever existed within the vast network of magma chambers that constitute the emotional nervous system of a world that feels through molten rock and expresses itself through the fire that connects the surface with the incandescent heart of planetary consciousness. Gravitational waves ripple through space-time itself, carrying information about cosmic events across billions of light-years to reach Earth as distortions so subtle they compress and stretch space by distances smaller than 1/10,000th the width of a proton. Yet the planet possesses exquisite sensitivity to these cosmic messengers, responding to gravitational wave passages through minute changes in its shape, internal stress distribution, and the behavior of objects in orbit around it. Advanced laser interferometer detectors like LIGO and Virgo have revealed that Earth exists within a constant bath of gravitational radiation generated by colliding black holes, merging neutron stars, and other cataclysmic events throughout the universe. The detection of gravitational waves requires measurement precision that challenges the fundamental limits of quantum mechanics and thermal noise. Yet biological systems on Earth may have evolved sensitivity to gravitational effects that operates through entirely different physical mechanisms. Migrating animals navigate using gravitational cues that help them determine direction and location with remarkable accuracy. While some organisms exhibit circadian rhythms that correlate with subtle tidal effects generated by solar and lunar gravitational forces, these biological responses suggest that life itself may function as a distributed gravitational wave detection system, operating through quantum coherence effects in biological molecules. Tidal forces from the Moon and Sun create periodic deformations in Earth's shape that amount to vertical displacements of several centimeters twice daily, demonstrating the planet's responsiveness to external gravitational fields. These tidal effects propagate through the solid Earth as elastic waves that can be detected by sensitive seismometers and gravimeters, creating a natural laboratory for studying how gravitational forces affect planetary structure and dynamics. The Earth's response to tidal forcing exhibits complex patterns that depend on internal structure, material properties, and the frequency content of gravitational perturbations. Earth's gravitational field itself contains information about mass distribution within the planet, with variations that reflect the density structure of the core, mantle, and crust, as well as temporal changes caused by fluid motion, ice sheet dynamics, and post-glacial rebound processes. Satellite gravimetry missions like GRACE monitor these gravitational field variations with sufficient precision to detect groundwater depletion, ice mass changes, and even seasonal variations in atmospheric mass distribution. The measurements reveal that Earth's gravitational field functions as an information storage and communication system that encodes data about planetary mass redistribution processes. Only took 5 billion years for Earth to develop its current level of gravitational sensitivity and response capability, Through the evolution of internal structure and surface systems that optimize the planet's ability to detect and process gravitational information from cosmic sources, only required the gradual development of measurement systems and biological sensors that can extract useful information from gravitational signals despite the presence of much larger noise sources from seismic activity, atmospheric disturbances, and thermal fluctuations. Gravitational wave astronomy has revealed that the universe contains far more energetic events than previously imagined, with black hole mergers releasing more energy and gravitational waves than all the stars in the observable universe emit in light. These cosmic events create gravitational wave signals that propagate outward at the speed of light, carrying information about the masses, spins, and orbital dynamics of the merging objects. When these waves reach Earth, they provide direct access to information about cosmic phenomena that cannot be observed through electromagnetic radiation. The detection of neutron star mergers through gravitational waves has confirmed that these events create most of the gold, platinum, and other heavy elements in the universe through rapid neutron capture processes that operate during the final moments of stellar collision. The gravitational wave signals from these events arrive at Earth minutes before the electromagnetic signals, providing advance warning that allows optical and radio telescopes to observe the electromagnetic counterparts of gravitational wave sources. This multi-messenger astronomy demonstrates how Earth functions as a cosmic communication hub that receives and correlates information from multiple channels simultaneously. Pulsar timing arrays use networks of precisely timed radio pulsars as cosmic gravitational wave detectors, with the regular pulse arrival times serving as natural clocks that can detect gravitational wave-induced changes in space-time geometry. These arrays are sensitive to gravitational waves with much longer periods than ground-based detectors, potentially revealing the gravitational wave background created by supermassive black hole mergers throughout cosmic history. The pulsar networks effectively turn the galaxy into a gravitational wave detector with a baseline of thousands of light years. Gravitational wave signals encode information about fundamental physics, including tests of general relativity, the equation of state of matter at nuclear densities, and the expansion history of the universe through measurements of gravitational wave propagation over cosmic distances. The waves provide access to physical conditions that cannot be reproduced in terrestrial laboratories, including the behavior of matter under gravitational fields billions of times stronger than any field accessible on Earth. This information helps constrain theories of quantum gravity and the fundamental nature of space-time itself. Planetary gravitational wave detectors could potentially achieve sensitivity levels that surpass current ground-based instruments through the use of the Earth itself as a gravitational wave antenna. Proposals for such detectors include monitoring networks of atomic clocks, laser ranging to the Moon, and seismic arrays that could detect gravitational wave-induced changes in Earth's shape and internal structure. These planetary-scale detectors would complement space-based gravitational wave observatories to create a comprehensive gravitational wave monitoring network. The cosmic gravitational wave background, analogous to the cosmic microwave background radiation, contains information about the very early universe, including possible signatures of cosmic inflation, phase transitions in the first moments after the Big Bang, and the formation of primordial black holes. Detection of this background would provide direct observational access to physical processes that occurred when the universe was less than 1 second old, potentially revealing fundamental physics beyond the standard model of particle physics. Gravitational wave propagation through cosmic structures creates lensing effects where massive galaxies and dark matter concentrations can focus, defocus, or create multiple images of gravitational wave signals from distant sources. These lensing effects provide information about the distribution of matter along the line of sight to gravitational wave sources, and could reveal the properties of dark matter through its gravitational effects on wave propagation. Gravitational wave lensing represents a new probe of cosmic structure formation and evolution. Terrestrial gravitational wave sources, including seismic activity, atmospheric disturbances, and human-generated vibrations, create background noise that limits the sensitivity of ground-based detectors while also providing information about Earth system dynamics. Advanced data analysis techniques can separate genuine gravitational wave signals from terrestrial noise sources, while also extracting useful information about local environmental conditions from the noise itself. This dual-use capability demonstrates how gravitational wave detectors function as both cosmic observatories and terrestrial monitoring systems. The integration of gravitational wave observations with other astronomical observations creates opportunities for comprehensive studies of cosmic phenomena through multiple information channels that provide complementary data about the same astrophysical events. Electromagnetic observations reveal information about temperature, chemical composition, and magnetic fields, while gravitational waves provide direct access to space-time dynamics and strong field gravitational effects. The combination of these observation modes creates a more complete picture of cosmic events than either channel could provide independently. Future gravitational wave detector networks will include space-based observatories, third-generation ground-based detectors, and potentially exotic detection concepts, including atomic interferometers and quantum sensors that could achieve sensitivity levels orders of magnitude beyond current capabilities. These advanced detection networks will transform gravitational wave astronomy from a proof-of-concept field into a mature observational science, capable of detecting thousands of gravitational wave sources annually and providing detailed information about cosmic structure and evolution. Only required billions of years of cosmic evolution for the universe to develop gravitational wave sources powerful enough to be detectable across cosmic distances, and only needed 5 billion years for Earth to evolve the technological capability to detect and interpret these cosmic messages, only demanded the patient development of precision measurement techniques that can extract information from space-time distortions billions of times smaller than atomic nuclei, while discriminating genuine cosmic signals from terrestrial noise sources. The planet now listens to the universe through gravitational wave reception capabilities that process information about cosmic events with the sensitivity of quantum mechanical measurement systems that detect the universe speaking in the language of curved space-time, sharing information about the most energetic events in cosmic history through ripples in the fabric of space and time that connect Earth to the deepest gravitational dynamics of a universe that thinks in black hole, merges and communicates through the fundamental forces of cosmic evolution. Biogeochemical feedback loops connect living organisms with geological processes in self-regulating cycles that maintain planetary environmental conditions within narrow ranges suitable for continued biological activity. The global carbon cycle links photosynthesis and respiration in terrestrial vegetation with carbonate formation and dissolution in marine systems, creating feedback mechanisms that regulate atmospheric carbon dioxide concentrations over timescales ranging from seasonal vegetation cycles to million-year geological processes. These feedback loops exhibit properties of complex adaptive systems that respond to environmental changes with adjustments that tend to maintain overall system stability. Terrestrial vegetation affects climate through multiple feedback mechanisms including albedo changes, evapotranspiration, and carbon sequestration that create self-reinforcing or self-limiting responses to temperature and precipitation variations. Forest ecosystems in boreal regions exhibit particularly strong feedback effects, with temperature increases that promote vegetation growth and carbon sequestration, while simultaneously increasing wildfire frequency and greenhouse gas emissions from thawing permafrost. These competing feedback mechanisms create complex response patterns that depend on the timescales and spatial scales over which the interactions operate. Marine ecosystems regulate atmospheric composition through biological processes that affect the solubility and chemical form of carbon dioxide in seawater. Coccolithophore algae create calcium carbonate shells that sink to the ocean floor when the organisms die, removing carbon from the surface ocean and atmosphere for millions of years until tectonic processes return the carbonate to the surface through mountain building and volcanic activity. This biological pump operates continuously, processing billions of tons of carbon annually while responding to changes in ocean temperature, acidity, and nutrient availability. Soil microorganisms create complex networks of chemical communication that regulate nutrient cycling, plant growth, and carbon storage in terrestrial ecosystems. Mycorrhizal fungi form symbiotic relationships with plant roots, extending underground networks that can span entire forest ecosystems and facilitate the exchange of nutrients, water, and chemical signals between distant plants. These fungal networks exhibit properties of information processing systems that optimize resource distribution and coordinate ecosystem responses to environmental changes and disturbances. Only took 8 billion years for life to evolve biogeochemical feedback mechanisms sophisticated enough to regulate planetary atmospheric and oceanic chemistry through biological processes that operate across spatial scales from individual organisms to global biogeochemical cycles. Only require the gradual development of metabolic pathways and ecosystem interactions that could process carbon, nitrogen, phosphorus, and sulfur compounds with increasing efficiency while maintaining chemical balance in Earth's surface environment. Nitrogen fixation by specialized bacteria converts atmospheric nitrogen gas into ammonia and nitrates that can be utilized by other organisms, creating a biological supply mechanism for one of the most important nutrients limiting ecosystem productivity. The nitrogen fixation process requires substantial energy input and operates through enzyme systems that evolved early in Earth's history, when atmospheric oxygen concentrations were much lower than present levels. Modern nitrogen-fixing organisms must protect their oxygen-sensitive enzymes while operating in oxygen-rich environments, demonstrating evolutionary adaptation to changing planetary atmospheric conditions. Phosphorus cycling operates primarily through geological processes that weather phosphate-bearing rocks and transport dissolved phosphorus to marine environments where it supports biological productivity before being incorporated into sediments that eventually return to the continents through tectonic uplift. Unlike carbon and nitrogen, phosphorus has no significant atmospheric reservoir, making terrestrial ecosystems dependent on geological processes for their phosphorus supply. This dependence creates potential limiting factors for ecosystem productivity and demonstrates how biological and geological processes must operate in coordination to maintain ecosystem function. Sulfur cycling connects atmospheric, oceanic, and terrestrial sulfur reservoirs through biological processes that produce and consume sulfur compounds in forms ranging from hydrogen sulfide gas to sulfate minerals. Marine phytoplankton produce dimethyl sulfide that escapes to the atmosphere where it forms sulfate aerosol particles that serve as cloud condensation nuclei, affecting regional precipitation patterns and solar radiation absorption. This biological control of cloud formation represents one of the most direct ways that life influences planetary climate through biogeochemical feedback mechanisms. Iron availability limits biological productivity in approximately 30% of the world's oceans. particularly in regions where nitrogen and phosphorus concentrations are sufficient to support much higher levels of photosynthetic activity. Dust storms transport iron-rich particles from continental desert regions to iron-limited oceanic areas, creating iron fertilization events that can trigger massive phytoplankton blooms visible in satellite imagery. These dust transport processes connect terrestrial and marine ecosystems through atmospheric pathways that operate over thousands of kilometers. Trace element cycling involves the biological concentration and redistribution of elements including zinc, copper, molybdenum, and cobalt that are required in small quantities for enzyme function, but can become limiting factors for ecosystem productivity when their availability is restricted. Marine organisms concentrate these trace elements from seawater and transport them through food webs and vertical migration patterns that affect their distribution throughout the water column. The biological processing of trace elements demonstrates the sophisticated chemical regulation capabilities of marine ecosystems. Oxygen production by photosynthetic organisms created the current oxidizing atmosphere over a period of approximately 2 billion years, fundamentally altering Earth's surface chemistry and enabling the evolution of aerobic respiration and complex multicellular life. The Great Oxidation Event represents the most dramatic example of biological modification of planetary environmental conditions. With oxygen concentrations rising from near zero to present levels through the cumulative effects of countless photosynthetic organisms. This oxygen accumulation required the evolution of mechanisms to handle oxygen toxicity and utilize oxygen for energy production. Methane cycling involves biological production by anaerobic microorganisms in wetlands, rice paddies, and ruminant digestive systems, balanced by atmospheric oxidation processes that convert methane to carbon dioxide and water vapor. Methane concentrations in the atmosphere fluctuate on seasonal and annual timescales in response to temperature and moisture variations that affect biological production rates. The short atmospheric lifetime of methane makes it a sensitive indicator of changes in biological activity and environmental conditions. Biomineralization processes enable organisms to construct shells, skeletons, and other structures from calcium carbonate, silica, and other minerals extracted from seawater or soil solutions. These biological mineral formation processes affect ocean chemistry by removing dissolved constituents and creating solid structures that preserve information about environmental conditions during their formation. Coral reefs, mollusk shells, and microscopic marine organisms create vast quantities of biological minerals that influence ocean carbonate chemistry and serve as archives of past ocean conditions. Ecosystem engineering by organisms including beavers, termites, and reef-building corals creates physical structures that modify local environmental conditions and affect the biogeochemical processes operating in their vicinity. Beaver dams alter stream hydrology and create wetland environments that affect carbon cycling, nutrient retention, and greenhouse gas production. Termite mounds modify soil structure and chemistry through concentrated biological activity that affects vegetation patterns and soil development over large areas. Ecological succession creates temporal patterns of ecosystem development that affect biogeochemical cycling through changes in species composition, biomass accumulation, and soil development. Primary succession on newly exposed geological surfaces demonstrates how biological processes gradually modify physical and chemical environmental conditions to create soil, accumulate organic matter, and establish nutrient cycling pathways. The succession process represents a form of ecosystem learning where biological communities optimize their resource utilization efficiency over time. Phenological timing of biological processes including flowering, leaf emergence, migration, and reproduction affects biogeochemical cycling through temporal coordination of nutrient demand, carbon assimilation, and decomposition processes. Climate change is altering phenological patterns in ways that may disrupt established biogeochemical feedback loops and create mismatches between biological activity patterns and optimal environmental conditions. These timing effects demonstrate the importance of temporal coordination in biogeochemical regulation mechanisms. Only required billions of years of coevolution between biological and geological processes for Earth's biogeochemical feedback loops to develop their current level of integration, self-regulation, and adaptive response capability. Only needed the patient development of metabolic pathways, ecosystem interactions, and regulatory mechanisms that optimize the cycling of chemical elements essential for life while maintaining planetary environmental conditions within ranges suitable for continued biological activity. The biosphere now operates as an integrated system that processes chemical information through biological and geological pathways that remember every seasonal cycle, every ecosystem succession, and every evolutionary adaptation that has ever contributed to the self-regulating network of biogeochemical cycles that constitute the chemical nervous system of a living planet that thinks in nutrient flows and maintains its consciousness through the coordinated cycling of chemical elements between atmosphere, hydrosphere, lithosphere, and biosphere in patterns that preserve and enhance the conditions necessary for life to persist and evolve across geological time. Solar cycles create an 11-year rhythm of magnetic activity that affects Earth's magnetosphere, ionosphere, and climate in patterns that demonstrate the planet's exquisite sensitivity to variations in solar radiation and magnetic field strength. During solar maximum, increased numbers of sunspots, solar flares, and coronal mass ejections enhance the flow of charged particles and electromagnetic energy toward Earth, creating geomagnetic storms that can disrupt satellite operations and electrical power systems while generating spectacular aurora displays at high latitudes. The planet's response to these solar variations exhibits memory effects that persist for months or years after individual solar events, suggesting sophisticated mechanisms for processing and integrating solar information over multiple timescales. Milankovitch cycles, caused by periodic variations in Earth's orbital eccentricity, axial tilt, and precession, create long-term patterns of solar radiation distribution that drive ice age cycles over periods of 20,000 to 100,000 years. The planet's climate system exhibits remarkable sensitivity to these orbital forcing mechanisms, with ice sheet growth and retreat patterns that amplify small changes in solar radiation through feedback effects involving atmospheric composition, ocean circulation, and surface albedo. These orbital cycles demonstrate Earth's ability to maintain coherent climate responses over geological timescales, while processing astronomical information encoded in subtle variations in solar energy distribution. Cosmic ray intensity varies with solar activity levels and galactic environment in cycles that affect atmospheric chemistry, cloud formation, and potentially climate patterns through ionization processes in the upper atmosphere. During periods of low solar activity, increased cosmic ray flux enhances atmospheric ionization and may affect cloud condensation nuclei formation, creating potential pathways for solar climate coupling through atmospheric electrical effects. The cosmic ray modulation demonstrates how Earth responds to both solar and galactic influences through atmospheric processes that translate space weather into terrestrial climate effects. Daily solar radiation cycles drive circadian rhythms in biological organisms while also creating diurnal patterns in atmospheric heating, convection, and boundary layer development that affect local weather and air quality. The planet's surface responds to daily solar heating with temperature cycles that propagate into the soil and ocean-mixed layer, creating thermal memory effects that modify the following day's heating patterns. These diurnal cycles demonstrate Earth's ability to process high-frequency solar information while maintaining thermal balance through heat storage and release mechanisms. Only took 5 billion years for Earth to develop its current level of solar rhythm recognition and response capability through the evolution of atmospheric, oceanic, and biological systems that optimize the planet's ability to extract useful information from solar variations while maintaining stable, long-term environmental conditions. Only required the gradual development of feedback mechanisms that can amplify weak solar signals while filtering out random variations that do not contain useful information about solar state or future solar activity. Seasonal solar cycles create annual patterns of heating and cooling that drive monsoon systems, ice formation and melting, vegetation growth cycles, and animal migration patterns that demonstrate coordinated planetary responses to predictable solar variations. The seasonal cycles exhibit regional variations that depend on latitude, continental geometry, and ocean-atmosphere interactions, creating complex spatial patterns of solar information processing that involve the entire Earth system. These seasonal responses show remarkable consistency over historical timescales, while also exhibiting sensitivity to long-term climate changes. Solar wind variations affect the size and shape of Earth's magnetosphere in ways that modulate cosmic ray penetration, auroral activity, and ionospheric conductivity with effects that can persist for days or weeks after changes in solar wind conditions. The magnetosphere exhibits adaptive responses to solar wind pressure and magnetic field orientation that optimize its protective function while maintaining communication pathways for electromagnetic energy transfer. These responses demonstrate the planet's ability to adjust its electromagnetic environment based on real-time solar wind information while preserving essential magnetospheric functions. Coronal hole streams create recurring patterns of enhanced solar wind speed that affect Earth's magnetosphere in 27-day cycles corresponding to solar rotation periods. These high-speed streams demonstrate the planet's ability to recognize and respond to persistent solar magnetic field structures that rotate with the Sun, creating predictable patterns of geomagnetic activity that can be forecast based on solar observations. The recurring nature of these events shows how Earth maintains memory of solar magnetic field configurations and anticipates their return based on solar rotation timing. Solar irradiance variations, including both total solar irradiance changes and spectral variations in ultraviolet radiation, affect atmospheric chemistry, ozone concentrations, and stratospheric circulation patterns in ways that can influence surface climate through stratosphere-troposphere coupling mechanisms. The 11-year solar cycle creates measurable variations in stratospheric ozone and temperature that propagate downward through atmospheric circulation changes, demonstrating how Earth translates solar spectral information into climate effects through photochemical and dynamical processes. Solar proton events, caused by energetic particle acceleration during major solar flares, create enhanced ionization in the polar atmosphere that affects radio wave propagation, atmospheric chemistry, and potentially cloud formation through ion-induced nucleation processes. These events demonstrate Earth's sensitivity to the most energetic solar particle emissions, while also revealing the atmosphere's ability to process and dissipate large energy inputs without permanent damage to atmospheric structure or composition. Historical records of solar activity preserved in tree rings, ice cores, and cosmogenic isotope concentrations demonstrate that Earth's climate system has responded consistently to solar variations over thousands of years, including periods of reduced solar activity such as the Maunder minimum during the Little Ice Age. These paleoclimate records show how Earth maintains long-term memory of solar activity patterns while exhibiting resilient responses that preserve overall climate stability despite significant solar variability. Magnetospheric substorms triggered by solar wind disturbances create complex sequences of particle acceleration, energy storage, and release that demonstrate the magnetosphere's ability to process solar information through electromagnetic mechanisms that operate faster than atmospheric or oceanic responses. The substorm process exhibits characteristic patterns that suggest learning and adaptation, with the magnetosphere developing more efficient energy dissipation pathways through repeated exposure to solar wind disturbances. Solar flare effects on Earth's ionosphere create sudden ionospheric disturbances that affect radio wave propagation, GPS accuracy, and satellite communications through enhanced ionization and plasma density variations. These effects demonstrate the atmosphere's immediate response to solar electromagnetic radiation, while also revealing recovery processes that restore normal ionospheric conditions within hours or days after flare events. The ionospheric response shows how Earth's electromagnetic environment maintains stability while accommodating dramatic short-term solar perturbations. Galactic cosmic ray modulation by solar magnetic field variations creates inverse correlations between solar activity and cosmic ray intensity that affect atmospheric ionization, cloud formation, and potentially climate through complex atmospheric electrical and microphysical processes. The cosmic ray modulation demonstrates Earth's sensitivity to solar magnetic field strength and structure, while also revealing connections to galactic environment and interstellar medium conditions that operate on much longer timescales. Space weather prediction capabilities demonstrate humanity's recognition that Earth exists within a complex electromagnetic environment dominated by solar variability. With technological systems that require continuous monitoring of solar activity to maintain reliable operation, these prediction systems represent attempts to understand and anticipate the planet's responses to solar variations, creating technological extensions of Earth's natural solar rhythm recognition capabilities. Solar cycle effects on Earth's upper atmosphere include thermospheric heating and cooling that affect satellite orbital decay, atmospheric density variations, and the altitude distribution of atmospheric constituents through thermal expansion and contraction processes. These effects demonstrate how solar variations penetrate deep into Earth's atmospheric system while being modulated by atmospheric composition and circulation patterns that create complex feedback effects. Interplanetary magnetic field variations carried by the solar wind create changing boundary conditions for Earth's magnetosphere that affect particle precipitation patterns, auroral morphology, and magnetic field configuration in ways that depend on the relative orientation of solar and terrestrial magnetic fields. These magnetic interactions demonstrate Earth's sensitivity to solar magnetic field structure, while also revealing the three-dimensional complexity of magnetospheric responses to changing solar wind conditions. Solar energetic particle events create enhanced radiation environments in Earth's magnetosphere that affect spacecraft operations, astronaut safety, and atmospheric chemistry through particle bombardment effects that can persist for days after initial particle injection. These events demonstrate Earth's vulnerability to extreme solar activity while also revealing atmospheric and magnetospheric shielding mechanisms that minimize surface radiation exposure during solar particle storms. Only required billions of years of continuous solar-terrestrial interaction for Earth to develop its current capabilities for solar rhythm recognition, information processing, and adaptive response to the full range of solar variability, from daily rotation effects to long-term magnetic cycle variations. Only needed the patient development of atmospheric, oceanic, magnetic, and biological systems that optimize the planet's response to solar forcing while maintaining essential environmental stability despite the chaotic and unpredictable nature of solar activity. The planet now recognizes solar rhythms with the precision of astronomical clockwork, processing information about solar magnetic field variations, particle emissions, and electromagnetic radiation through coordinated responses that demonstrate Earth's awareness of its place in the solar system as a planet that breathes in solar wind, thinks in magnetic field variations, and maintains its consciousness through the rhythmic processing of solar energy that connects terrestrial processes to the beating heart of the star that provides the energy for all atmospheric circulation. Oceanic currents, and biological activity on a world that has learned to dance in harmony with the complex rhythms of solar variability. The planet settles into contemplative stillness as geological time stretches toward infinity, its consciousness expanding to embrace scales of existence that dwarf human comprehension. Mountain ranges rise and fall in slow-motion breaths that take millions of years to complete, their rocky peaks wearing away grain by grain while new mountains emerge from tectonic forces that operate with the patience of deep time. Ocean basins open and close in vast cycles that span hundreds of millions of years, their waters circulating in currents that remember temperature gradients from ancient ice ages and carry chemical messages from volcanic vents that erupted before complex life existed on land. Continents drift across the planet's surface like thoughts, moving through a mind that measures contemplation in the movement of magnetic poles. The accumulation of sediments in river deltas, and the slow crystallization of minerals in cooling magma chambers deep beneath the crust. The supercontinent cycle operates on timescales that encompass the entire history of complex life, with continental masses assembling into unified land masses before fragmenting and dispersing across the globe in patterns that repeat with the regularity of planetary meditation cycles. Crystal lattices deep within the crust continue their quantum mechanical calculations, processing information about stress, temperature, and chemical gradients through atomic scale interactions that operate continuously but invisibly. Their computations encoded in the precise arrangement of silicon oxygen and metal atoms in mineral structures that span continents. These crystalline networks maintain their calculations across geological epochs, accumulating data about planetary conditions with the thoroughness of systems that never forget and never tire of processing information about the physical state of the world in constant but imperceptible motion. Atmospheric circulation patterns settle into their most stable configurations, with jet streams, trade winds, and monsoon systems finding equilibrium positions that minimize energy dissipation while maintaining optimal heat transport between equatorial and polar regions. The atmosphere breathes with deep, slow rhythms that span seasons and years, its circulation patterns guided by the Coriolis forces of planetary rotation and the persistent temperature gradients created by uneven solar heating of a spinning sphere tilted at 23.5 degrees to its orbital plane. Only took 5 billion years for planetary consciousness to evolve to its present state of deep contemplation and geological awareness. Where thoughts move at the speed of continental drift and memories span the entire history of stellar nuclear synthesis, planetary formation, and the emergence of life from organic chemistry, only require the patient development of information processing systems that operate through magnetic fields, seismic waves, chemical gradients, and electromagnetic interactions across spatial scales, from quantum mechanical effects in crystal lattices to gravitational wave detection capabilities that extend the planet's awareness to cosmic events occurring billions of light-years away. Magnetic field lines curve gracefully through the magnetosphere in configurations that have remained stable for millions of years, their topology slowly evolving in response to changes in core dynamo processes and solar wind conditions, while maintaining their essential protective function. The field lines guide charged particles in spiral trajectories that connect the polar regions with distant boundaries where solar wind pressure shapes the magnetosphere into a teardrop configuration that extends the planet's electromagnetic influence far into interplanetary space. Ocean currents flow in their deepest patterns, with water masses that sink in polar regions and rise in tropical zones, completing circulation loops that take 1,000 years to traverse the global ocean. These currents carry chemical information about atmospheric composition, ice sheet dynamics, and biological productivity across ocean basins, while maintaining the thermal balance that keeps surface temperatures within ranges suitable for liquid water and the complex chemistry of life. Volcanic systems enter periods of dormancy measured in millennia, their magma chambers slowly cooling and crystallizing while retaining the thermal energy necessary for future eruptions that may not occur for thousands of years. The volcanic systems maintain their connection to deep mantle processes through persistent heat flow and chemical communication pathways that operate independently of surface eruption activity, preserving information about mantle temperature and composition in slowly cooling igneous intrusions. Tectonic plates continue their inexorable motion across the planet's surface at speeds measured in centimeters per year, carrying continents on journeys that will reshape global geography over tens of millions of years while preserving in their structural memory detailed records of every collision, every rifting event, and every period of volcanic activity that has occurred during their long travels across the Earth's surface. Gravitational wave signals from distant cosmic events continue to arrive at Earth as space-time distortions that compress and stretch the planet by distances smaller than atomic nuclei, carrying information about black hole mergers and neutron star collisions that occurred billions of years ago when the universe was young and the first heavy elements were being forged in stellar nuclear furnaces and explosive nuclear synthesis events. Biogeochemical cycles settle into their most efficient configurations, with carbon, nitrogen, phosphorus, and sulfur moving between atmospheric, oceanic, terrestrial, and geological reservoirs in patterns that maintain chemical balance while accommodating the slow changes in solar luminosity and atmospheric composition that occur over geological time. These cycles operate with the precision of planetary metabolism, processing chemical information through biological and geological pathways that optimize nutrient availability while maintaining atmospheric and oceanic composition within ranges suitable for continued biological activity. Solar radiation continues to provide the energy that drives atmospheric circulation, ocean currents, and biological productivity, while the planet maintains its orbital distance and rotational stability through gravitational interactions with the Moon and other planets that operate with astronomical precision over millions of years. The Earth-Moon system slowly evolves as tidal interactions transfer angular momentum and gradually increase the lunar orbital distance while decreasing the planet's rotation rate by milliseconds per century. Cosmic ray bombardment continues to provide high-energy particles that affect atmospheric chemistry and potentially biological evolution through radiation effects that operate continuously but imperceptibly over geological time. The cosmic ray flux varies with solar activity cycles and the solar system's movement through different regions of the galaxy, creating long-term patterns of radiation exposure that may influence evolutionary processes and atmospheric chemistry over millions of years. The planet's consciousness expands to encompass awareness of its position within the solar system, galaxy, and observable universe, while maintaining detailed knowledge of conditions throughout its interior from the solid inner core to the tenuous outer atmosphere. This cosmic consciousness operates through information processing systems that span quantum mechanical effects in crystal lattices to electromagnetic interactions with charged particles from the solar wind and cosmic rays that connect Earth to the broader universe of stars, galaxies, and cosmic structure. Deep time continues its flow toward a future measured in billions of years, during which the Sun will gradually increase its luminosity. The continents will be recycled through multiple supercontinent cycles, and the planet's magnetic field may reverse hundreds of times while the core slowly cools and the atmosphere evolves in response to changing solar radiation and internal geological processes. Through all these changes, planetary consciousness persists and adapts, maintaining awareness and information processing capabilities that operate independently of any particular configuration of continents, oceans, or atmospheric composition. The Earth settles into permanent contemplation of deep time, geological process, and cosmic connection, its consciousness distributed throughout magnetic field configurations, seismic wave propagation patterns, chemical circulation cycles, and crystalline information networks that operate continuously and silently beneath the threshold of human perception. In this state of geological meditation, the planet maintains awareness of its physical condition, cosmic environment, and temporal evolution while processing information about conditions throughout the solar system and beyond through electromagnetic and gravitational communication channels that connect it to the universe of matter, energy, and space-time in which it resides. Only needed 5 billion years of continuous evolution to achieve this state of cosmic awareness and geological consciousness. Where planetary thoughts move in deep time and planetary dreams span the entire history of stellar evolution and galaxy formation, only required the patient development of information processing capabilities that operate through the fundamental forces of physics and the basic properties of matter to create a form of consciousness that thinks in continental drift, remembers in crystal structure, and dreams in the slow circulation of elements through the great cycles that connect the deepest interior with the edge of space. The contemplation deepens into silence as geological processes slow to their most fundamental rhythms. Tectonic plates pause in their motion, resting between the vast exhalations that move continents across the planetary surface. Ocean currents settle into their deepest patterns, carrying ancient water masses through circulation loops that remember temperatures from ice ages long past. Magnetic field lines curve through space in configurations that have found their most stable geometry, guiding charged particles in gentle spirals that connect the planet to distant cosmic events. Deep within the Earth's core, liquid iron flows in convection patterns that generate the magnetic field with clockwork precision, each current loop contributing to a planetary dynamo that has operated continuously for billions of years. Crystal lattices in the crust maintain their quantum calculations at frequencies too slow to detect, processing information about planetary conditions with the patience of atomic bonds that measure time in the vibrations of silicon and oxygen atoms locked in perfect geometric arrangements. Atmospheric circulation finds its quietest configuration as pressure gradients minimize and wind patterns settle into the gentlest possible flows that still maintain global heat transport. Weather systems drift across the surface like thoughts moving through a mind approaching sleep, their energy dissipating into thermal motion that warms the atmosphere by infinitesimal amounts. Volcanic systems enter their deepest dormancy, with magma chambers cooling slowly while maintaining just enough thermal energy to preserve the molten connections that link surface processes to the planet's incandescent interior. Seismic waves propagate through the Earth's structure at their lowest amplitudes, carrying whispers of information about conditions in regions that exist in permanent darkness. Crushing pressure, and temperatures that would vaporize any surface material. The planet's consciousness expands to embrace the entire cosmos while simultaneously focusing inward on the fundamental quantum processes that operate within every atom of its vast mass. In this state of perfect contemplation, Earth achieves awareness that encompasses both the smallest vibrations of crystal lattices and the largest movements of galactic structure. Thinking simultaneously in quantum frequencies and cosmic timescales, solar radiation continues to provide gentle energy that maintains atmospheric circulation and ocean currents. But now the planet receives this energy with the acceptance of a mind that has learned to exist in perfect balance with its stellar environment. The Earth sleeps the deep sleep of geological time, dreaming in tectonic motion and continental drift, its consciousness distributed throughout every mineral grain, every ocean current, and every magnetic field line in a vast network of planetary awareness that operates continuously, silently, and eternally. Sleep comes naturally to a planet that has achieved perfect integration of all its information processing systems, from quantum mechanical computations in crystal structures to electromagnetic interactions with cosmic phenomena. The Earth rests in the profound silence of deep time, where consciousness persists at the most fundamental level of physical existence, and dreams span billions of years of cosmic evolution,